Thank you for being here today. So the first speaker is Ulderico Fugacci from the Riihimäki in Genova. He's going to talk about topology versus learning, a preliminary comparative study. The word is yours. Thanks.
Thanks a lot for the introduction. Thanks to all of you for being here. Yes, I have chosen this a bit provocative title for present you a simple comparison between different methods. Some of them are rooted in topology, specifically topological data analysis, and even more specifically on persistent homology, versus some methods based on learning, machine learning, and deep learning. And then we will try to combine in a very naive, in some sense, manner, this method to understand if the combination of these approaches could increase the obtained performance. I decided to speak about a preliminary study because in some sense it is still far to be completed. I mean, today we will see a sort of first example, a first case of study on which these methods have been performed. But on the other side, I try to force myself to apply the simplest possible methods, both in topological data analysis and in machine learning. This is done for a reason. I mean, in the last year, at least the last 5 years, something like that, the combination of topological data analysis and learning, I mean, is much more growing, and it is plenty and of interesting papers and sources in which this combination of methods produce very interesting and effective results. Today, I would like to go in the exact opposite spectrum of the topic, and I would like to present you a very naive and simple, and in some sense also simplistic analysis of the problem. All these study start from a question that several times has been asked. We are at the conference of Combinatorial Algebraic Topology and Application. So most of us are exactly in the middle of application and more theoretical stuff. And every time when we have to transfer our knowledge in a real application and experiments, at least I experienced some resistance in applying topological methods in real world application. And typically the data scientist, the computer scientist, does not understand or prefer not to use topology because it's a little bit too theoretical. It requires maybe some more efforts. And so it is not simple to explain why integrate topology in a data analysis. On the other side, it is possible to find a person very rooted in theory that does not understand the efficiency and the effectiveness of learning methods. And so these analyses want to provide a very simple and naive analysis trying to give an answer to these questions, and on the same time also help us to understand which are the key ingredients that distinguish and characterize these two classes of tools in order to properly understand the specific feature of each of them, and then use these elementary bricks to build something much more complicated. So actually, when I received the invite for this conference, I mean, I thought that could be, I mean, this preliminary analysis could be a good starting point for a discussion for you. So you will see several limitations in this analysis. Some of them are due to the fact that, I mean, the work is still in progress. Some others, I mean, are due to choices that we can discuss together. But yes, I would like to present this more as a, I mean, it is not a result, it's more a way to start a discussion with you. So I hope this could be the beginning of a discussion rather than the presentation of a result. So feel free to interrupt me anytime now, but even in the coffee break and later. Let me give you a short outline of the talk. First of all, we present the data sets on which we perform our analysis. The goal will be to classify images. We will focus on two classes of images, a data set based on, I mean, presenting some surfaces that could be cracked or non-cracked, and the other one, a data set in which there are some cells that could be infected or not by malaria. I mean, I have no expertise on none of these domains, so I mean, uh, I mean, so I simply consider them as images, and so uh, I don't think that the tool that we developed could seriously, I mean, help the the study in malaria or something like that. But I mean, there are just two cases of study on which perform our tools. Then I will present the methods that we have considered in our analysis. As I mentioned, there will be some topology-based approach and then some learning techniques, machine learning and deep learning tools. And as I mentioned, then we will try to combine a little bit these techniques to understand if the combination produce interesting results or not. Again, as I mentioned, I try to make this analysis replicable to everyone. So I decided to adopt the most available and most simple tools in each of these fields. Then we will analyze the result. We will see some comparison. Hopefully, we will, I mean, draw some conclusion, and I mean, we could discuss some future direction. So let's focus on the data sets. We decided to adopt two public data set of images. As I mentioned, the crack data set and the malaria data sets. I mean, the goal was to identify cracked surfaces in one case and parasitize cells on the other case. In all the learning processes, we split our data set by adopting the most common splitting that one can imagine, still for maintaining a very elementary approach. So 80% of training, 20% of which devoted for validation, and 20% of testing. Of course, topology-based method, which will not require a training, I mean, only consider the test set. But give a closer look to these data sets. So the crack data sets, it's a public domain data set containing 40,000 surface images. As you can see, they represent wall surfaces in different line, finishing, and roughness condition. And the data sets is equally split between cracked, positive, and non-cracked, negative images. And as you can see, the task is not so difficult, at least for these considered images, because I mean, it's pretty simple, at least at a naked eye, to distinguish which surfaces are cracked or not. But of course, the automatization of this process could be quite useful. Still for working with, I mean, to focus on the result more than the efficiency, we decided to reduce the size of these images to a smaller size. So the images will be reduced to resize to 64 times 64 pixels. But I mean, this is nothing crucial for the analysis, I think. The other data sets instead contain slightly less images, 28,000, taken from infected and healthy individuals. Also, in this case, the examples are equally splitted in two classes, parasitized cells and uninfected cells. Also, if you see some color discrepancies in the images, this is due to different condition in the acquisition. And as you can notice, malaria, cells infected by malaria present these blood stains that could be signal for the presence of malaria. I will start immediately with two possible limitations. Why just consider just images? And if you notice, the task of distinguishing positive and negative images in both the cases, the images present somehow a clearly distinguishable topological signature, in the sense that you can easily notice that cracked surfaces typically have these lines, this curve separating in two main components the data set, while these spot, this stain also can be could be turned into clear topological features that can be distinguished from images which does not present these stains. So both in some sense are limitation, but again, for the sake of simplicity, we decide to focus just on images. Of course, future step will, in the future step, we would like to include also different data sets. I can imagine graphs or point clouds simply. And concerning the second point, probably you are not the best audience for, the goal of this talk is also to present this kind of analysis also to people not expert in learning or not expert in in topological data analysis. And so, the choice for a data set with a clear topological signature was done especially for helping people not expert in topology to understand which kind of feature can be extracted from images. But of course, all of us work with topology and know that several times topology is able to capture features that are invisible at the naked eye. And so also integrating a different case of study with these characteristics could be interesting in the future. Let's focus now on the considered methods. We will speak about persistent-based approaches, machine learning approach, deep learning techniques, and hybrid methods. Let's start describing the persistent-based methods. This slide, I think, is completely useful for you in the sense that, we all know homology and its capability of detecting the holes of a shape, of a topological space or a simplicial complex. And persistent homology is just somehow the evolution of homology, able to detecting the changing in homology of a filtration of shapes. So instead of capture the homology of a single frame of this filtration, we keep track of the birth and the death of topological features of the holes of this filtration across the time, across the parameter filtering our complex. And so what we get are persistent pairs, which are nothing but pairs of values representing the birth of the death of this topological feature that could be represented as we seen yesterday by intervals. So the pair of value represent just the extrema of an interval, or could be collected as a collection of points in the plane. So the pairs of value represent just the coordinates of these points. And in this case, in the first case, we will speak about persistent of barcodes, while in the second case, we will speak about persistent diagrams. So let's see how we apply persistence to our data sets. First of all, we produce a binarization of our images from a grayscale images. We turn it into a black and white image. And this black and white image is considered as a collection of points in R2. Black points will be considered as point. And then we apply a Vietor-Rips complex filtration for building a filtration of simplicial complexes. These filtration of simplicial complexes will be turned into a persistent diagram. We extract the persistence of this filtration. And so in the end, from an image, we extract a persistent diagram. In the case of these cracked surfaces, we decided to also add a black boundary in order to, help the classification, in the sense that, as we will see, cracked surfaces will be characterized by a situation in which there are two clear one cycles, homological one cycle appearing in the filtration with a, relatively high persistence. Of course, even in the case that this crack is not exactly complete, side to side, the persistent homology, sì, no? Consentiamolo? Ma sì, non dovevo farlo. Niente, non è successo niente. Even if when the crease is not complete, persistent homology is able to capture the fact that there is a crack in the surface. So let's see, 4 different examples. And so a positive example of a surface cracked, a non-cracked surface, infected malaria cells, and non-infected cells. As you can see, the persistent diagram that we extract have a pretty clear topological signature. Cracked datasets present multiple H1 persistent homology feature, while a non-cracked surface present just one cycle. And the same for malaria datasets, not exact. So if we have more than one H1 persisting feature, they will be classified as infected, while non-infected cells present just one. Please. No, in the sense that for what we did, in some sense, the stains are converted in holes somehow, and so we capture the number of holes. You mean here? This one? No, in the sense that yes, we adding the boundary. Actually, we we create these two walls, and the addition of this border actually is for that. Okay, so and yes, something that I didn't mention clearly is the fact that in the analysis that we will see, we will just consider H1, because in this case, actually, we try we try different way for binarization. Then we adopt some standard algorithm in the literature. We try to consider adjacent cells to understand their color and stuff like that. And then I don't remember exactly which tools we adopted, but we decided to go with what we consider the most standard tools in the literature in order to maintain the simplicity that and the replicability that I mentioned. So, but we try different threshold and stuff like that, but in the end, at least for these data sets, the parameters for this binarization does not affect so much the final result. So what we get is we get a persistent diagram from an image. So for each image, to each image, we associate a persistent diagram. And in order to distinguish and classify these diagrams, we have to compare them. We did that in two different ways. The second one is considering the bottleneck distance between persistent diagram, or better, between a persistent diagram and a reference persistent diagram that could be considered as the reference for a non-cracked surface or an uninfected cell. And this is, slightly time consuming, at least more time consuming than just simply consider the persistent diagrams and counting the number of holes of classes that persist more than, much more than the others. And so in the case of cracked datasets, we will consider a surface cracked if the number of H1 persistent classes is strictly greater than 1. And in the case of the malaria, we'll consider a cell infected if the number of H1 persistent classes is strictly greater than 0. So we adopt these two classification tool for discriminate the obtained persistent diagrams. So in the end, this is the pipeline adopted for the two persistent homology-based approaches, from image to filtration, from filtration to persistent diagrams, and then we compare persistent diagram, which, adopting one of these two strategies. Concerning machine learning approaches, again, we decided to go with the more vanilla, the more classical tools, at least for my knowledge, in machine learning. So we directly apply this tool on raw images, and we adopt logistic regression, which is able to estimate class probability. And it's quite effective for nonlinear decision boundaries. We adopt support vector machines, which are able to identify hyperplane, maximizing the separation between the classes. And we adopt random forest, which are able to reduce the overfitting that one can get if focus on decision trees. So obviously we apply these three tools independently, and so we have three different standard and classic machine learning tools. Concerning deep learning approaches, I would like to say that I'm not a real expert, but studying a bit the literature, I think that the four method that we consider are pretty well settled in the literature. I mean, of course, while we are speaking, there are methods that have been developing that are maybe much more effective than this one, but these four are the four that we consider as four standard methods for image classification in deep learning. All of them have different capabilities and features. I don't think that I want to go into details. I mean, some of them are simply usual convolution filters. Others introduce, in one case, this residual connection. In the other case, this inception V3 is famous for these inception modules that allow to capture multi-scale information in the data, while the third one is particularly effective in a scenario where we have, mobile application. I mean, it's very light and efficient, and so it's specifically designed for mobile application. So we consider persistent-based approaches, machine learning approaches, deep learning approaches, and then we play a little bit. Wait a second. A crucial aspect in the deep learning approaches is the choice of a set on which we pre-train our model. This is a crucial step, as we will see, and we decided to consider ImageNet, which is a huge data set containing millions and millions of labeled images on which pre-train the models that I show you in the slide before. This is a step that I considered more or less trivial, and I didn't put a serious investigation of this aspect, but it turned out to be one of the more crucial aspects in this analysis, because the selected data set for pre-training the models contain mainly images of natural scenarios. I mean, images coming from natural categories, so animals, plants, and stuff like that. And there were some similarities with the images of the cracked dataset, while the images which are in this set are quite different by the images of the malaria datasets. And so there is, in some cases, there are some domain similarity for the first case of study, while there are there are a lot of difference with respect to the malaria datasets. And we will see in the result that these will be maybe one of the most crucial parameters that will affect the final evaluation. Okay, considering hybrid approaches, again, we prefer the most natural choice for combining learning methods and persistent-based homology methods. We simply decided to apply machine learning techniques to persistent diagrams. Of course, in order to do that, we have to vectorize, to turn into vector our persistent diagrams, and we simply did that by using persistent images. And so persistent images somehow rotate our persistent diagrams and transform it into an image. And the machine learning techniques that I considered before, the logarithmic regression, the support vector machine, and the random forest, are performed on these persistent images rather than straight on the images of the datasets. So in this case, this hybrid approach consider the dataset, extract the persistent diagrams as before, then convert these persistent diagrams into images, and then the three machine learning methods that we applied before for raw images will be applied for these persistent diagrams, for these persistent images. So I think that now we have more or less all the all the ingredients which have been used for the analysis, and we are ready for showing you the results. Again, we try to adopt available tools in the literature and well-settled libraries in the literature. And so we simply use scikit-learn, Ripser, Persim, TensorFlow, stuff like that. If you want the code and our experiment are available online. And in our analysis, we adopt some pretty standard metrics to evaluate our results. I mean, in the following, we will see tables considering all these metrics. We mainly, for simplicity, consider just, accuracy during the talk of today. But of course, if you want, we can discuss also about the other evaluation metrics. For making our analysis a little bit more interesting, we decide to work on a parameter. So, and the parameter is the number of sample per class that are available for the training. So we decided to consider from 1 to 500 sample per class in the training sets. So when we consider 1, this simply means that we provide in the training process just 2 images to the model, 1 positive and 1 negative. Of course, this is a pretty a limitation, but of course, we decided to go from 1 to 500, which 500 is 1,000 images on which training our models. So let's see what which are the performances of the methods. And of course, this parameter does not play a role for persistent-based methods, since persistent methods are direct methods, and there is not a training process for that. Let's focus on persistent homology-based methods. You see here cracks and malaria datasets. And the 2 lines represent the 2 different ways for comparing persistent diagram, just counting the hosts that persist or comparing them via bottleneck distance. The results for, considering the case that we apply a very simple tools and pretty elementary tools are pretty interesting. And also simply counting the hosts that persist is slightly less efficient than considering the bottleneck distance, but still is able to obtain pretty interesting values. The same is confirmed by these confusion matrices that help us to understand how the positive and negative predicted and actual classes have been classified as positive or negative. Let's try to include in the analysis also the machine learning techniques. This is a quite complicated table, but is much easier than you can thought. So the first bunch of columns represent the machine learning methods, while the second bunch of columns represent the same machine learning methods, but applied on the persistent images. So these are the hybrid methods. This is the machine learning methods. Each line represents a different machine learning method, so logistic regression, support vector machine, or random forest, and each cluster of line represent different values for the parameter representing the number of samples per class. So as you can see, for just 1 sample per class, we obtain not so satisfying result, around 69% of accuracy. But of course, as long as we increment this number of samples, we obtain much more effective and accurate result. On the other column, bunch of column, you can see that the introduction of persistent images, make the result more or less independent, or at least much less dependent from the choice of the numbers of sample per class. Because still by adopting a very low number of sample per class, we obtain a very nice results. And of this is the accuracy, precision, recall, and the F1 score, which is the harmonic mean of the precision and the recall. I mean, for simplicity, you can just focus on the accuracy. I mean, there is, the result of the accuracy are pretty representative of the other columns. And the accuracy is just how good we are in, are good are our prediction. So the percentage of correctly predicted images. So in this case, the 91% of the time we give a correct answer, while in this case, the 96% of the time we give a correct answer. This is the same table as before, but represented as a graph. Maybe is much more readable for you. The green line, I don't know if you can see the green, this constant line represents the result that we obtained by persistent homology, that of course does not depend from the number of samples, and so this is constant. The dotted line represent the machine learning methods that, as you can see, improve their performances as long as we increase the number of samples. And the non-dotted, the solid lines represent the method combining machine learning and persistent homology. And also in this case, there is a growing behavior, but since the beginning, we obtain pretty satisfying result with respect to the result that we can obtain by simply considering machine learning methods not hybridated with persistent homology. We have a similar scenario also for the malaria datasets. What I showed you before was focused on the crack dataset. In this case, what we get is that the machine learning methods, the pure machine learning methods, struggle a little bit in reaching the results that one can get by the simple persistent homology or the combination of persistent homology and machine learning. So in this case, we should somehow consider a much higher number of samples per class in order to see if this method could reach and overcome the methods based in persistent homology or the hybrid methods. But so the behavior is the same as before, but the machine learning method here are not able to, to be comparable with the methods that include the persistent homology in the analysis. Let's introduce now also the deep learning methods, and let's focus on the crack datasets. Again, you can focus just on the first column, representing the accuracy. The numbers here represent the increasing number of samples per class considered, and each single line represents a different method adopted in deep learning. Again, in this case, you see that the accuracy improve while we increase the number of samples, but since the beginning, at least certain models achieve pretty interesting results. And so this is the situation. So again, the green line represent persistent homology. The blue line represent the best hybrid models combining persistent homology with machine learning, while the dotted line represent the 4 different deep learning models that we adopted. And you can see, I mean, since 3 in most of the case, but definitely after 25 sample per class, the deep learning methods are much more accurate in predicting the images. Of course, in all the cases, we get pretty interesting accuracy values, but at a certain point, more or less, deep learning approaches reach more or less the perfection, 99% of accuracy. This is the same results expressed via different visualization. And as you can see, I mean, this line represents the result achieved by persistent homology. And after a while, all the learning methods beat or achieve better result than persistent homology. This is the case for crack dataset. The same is no longer true for malaria dataset. I mean, rather than showing this, I will show you this. So again, the dotted line represents the deep learning methods, while the solid line represent the methods based on persistent homology or containing at least persistent homology. In this case, even if we increase the number of sample, we are not able, in certain cases, of reaching the accuracy of persistent homology. And we thought a little bit about that. And what we think is that the first reason for that is to be, has to be searched in the choice of the pre-training set. The fact that there was a sort of domain shift between the image of the pre-training set and the image of the malaria datasets probably is the cause of this lack of capability in the in the deep learning methods. So this is something that people from data science always repeat: how is important, how is crucial the choice of proper data, how is crucial the goodness of the considered data. But every time, in some sense, I forgot, but I underestimate the consequence of a good choice, of a good or a bad choice. And as you can see, this was somehow surprising for me. We achieve incredibly good results for the crack datasets using deep learning approaches, while in this case, except for one method, the other methods struggle in achieving decent results. So these are a sort of summary of the previous charts. Again, green line represent persistent homology, blue line represent the best hybrid model, and the dotted line represent learning approaches. In this case, this is the machine learning approach, the best machine learning approach, and this is the best deep learning approach. While in this case, yes, again, this is the best machine learning approach, and this is the best deep learning approach. Of course, one crucial parameter in our analysis is this number, the number, the parameter that consider the number of samples per class in the training sets. And of course, something that we would like to do in the future is to extend this graph, considering much higher values. But this is a table somehow comparing different methods and trying to tell you if the adoption of machine learning method is better or not than some persistent-based method. But of course, I mean, probably the previous charts are much better, much more expressive somehow. Let's try to draw some conclusion. In a nutshell, topological methods actually obtain somehow surprisingly good results, uh, especially in case of data scarcity. I mean, the number of sample per class that we consider represent the number of labeled images that we have in our data set. And so, of course, there are situations in which having just 500 labeled images, it's a very limited number of images to be work on. And so, I mean, I assume that if your goal is to classify cats and dogs, this number is not realistic. But that number is much more realistic in case where maybe the domain is pretty specific or is related to some medical images in which it's not possible that a common person, I mean, is able to classify positive and negative example, but we need maybe an expert, a domain expert to do this labeling process. And so in certain domains, the number that we have considered could be also considered as high numbers of a sample per class. Deep learning methods, of course, provide very good result, but under two conditions. So a reasonably high number of sample per class in the training set, and the second parameter that I underestimate at the beginning of this analysis, the fact that the pre-training of these models play a crucial role in the goodness of the final results. Of course, maybe for people more expert in learning than me, what I'm saying is completely trivial. But I mean, at least these are some limitation of deep learning methods that topology, is not affected by. And another thing to say that in high sample regimes, actually, both methods, all the class of method that we have analyzed produce a good result, and there is not a clear winner. Okay, let's try to draw some conclusion. I mean, we produced this comparative analysis. As I mentioned, our goal was to adopt a very simple, well-settled, and not complicated tools to have a sort to produce an analysis from scratch somehow, because several times we see that I needed for this comparison, because several times that the other comparison that I see in the literature consider maybe very specific case or pretty complicated models, both concerning learning methods and persistent homology tools, while I would like to produce an analysis that could consider the most elementary techniques on the both sides. Of course, there are some limitation in our analysis. Some of them are done by the choices that we have done. And of course, all of them could be improved in the future. Could bring to some improvements. Of course, the first thing that I would like to do is to consider different kind of data, so not only images. Then I would like to consider also data sets in which it's not so easy for a topology at the naked eye to classify images. So in which I would like to consider data sets in which uh, the topological features are not so evident, are not so prominent. And this could be interesting also for a data scientist, a computer scientist, because working with the application, we are aware that in several cases, it could happen that topological feature does not bring us a a remarkable information, but there are also several cases in which, at the first glance, the dataset does not contain topological feature, but then once we extract persistent homology, we understand that the topology actually play a crucial role in the dataset and contain and convey crucial information of the dataset and provide good result in classification. And another thing that I would like to do is to include other methods. As you can see, we have not considered integration between persistent homology and deep learning approaches. On one side, we were already satisfied by the result that we achieved by combining persistent homology and machine learning. So it seems to us a little bit unnecessarily to combine persistent homology also with deep learning methods, but it's something that I would like to do in the future. As I mentioned, this is not a real talk, it's just a way to start a conversation for you. So, I will point out you to our paper in which we present in more detail this analysis. It has been amazing because by chance I had the opportunity to work with two twin brothers, one expert in topology and no knowledge in learning, and the other one expert in learning and no knowledge in topology. And so it has been quite instructive. And I wish to thank you, the foundings that allow this kind of research, and also you that you listen to me. So feel free to ask me anything, and I hope this could be a good starting point for a discussion. Thanks a lot. And sorry for, my presentation. I am aware that my presentation, it has been quite different than maybe the other ones that we see in the previous days. I would like to, I like theorems, but today I would like to provocate a little bit you with this kind of talk. Thanks you.
Questions?
Non essere cattivo, Eloy.
Thank you for your talk. I have a question regarding in the graphs you showed regarding the hybrid methods. The accuracy seems to stay almost constant for both persistence-based and the hybrid methods, independently of the amount of samples. My question is there any advantage in terms of faster loss decay or something you can see in the training phase? Is there any reason for using more samples with these approaches?
Actually, no. Yeah, yes, yes, yes. We play a little bit with all the parameters, and yes, we don't see any real advancement on, picking some parameter respect to others. And yes, we play a little bit with all these values and strategies, but in the end, yes, the result that we get are essentially comparable with the one simply conveyed by the standard persistent homology approach. And once you consider a reasonable number of sample per class, they are more or less indistinguishable. Actually, also in that case, persistent images, are just images containing I don't know if you can see that containing the points of the persistent diagrams. And so comparing them by bottleneck distance, by just simply counting the number of dots up to a certain threshold, or comparing these images as images, I mean, all these methods are more or less equivalent in some sense. Thanks.
Okay, thank you.
One more.
Did you binarize the data before you fed it into the machine learning tasks as well?
No.
Okay.
No. For machine learning and deep learning process, we apply the methods on the raw images. But yes, this is something that we didn't consider, but probably it could play, yes.
Because once you binarize the data, the task is essentially becoming, is there a white dot on the image?
Yeah.
Which for a machine learning task should be quite easy. There's also
Yeah.
for the persistent images. So I suspect that if you binarize the data before you feed into the machine learning, then your accuracy will start to match the TDA approach.
Yes, you're right. Thanks.
Thanks. Further questions? If not, let's thank the speaker again. So the next speaker today is Henri Riihimäki from Nordita. He's talking about Avalanche complex and topology with sandpile dynamics and digraphs. The board is yours.
All right. Thanks, Luigi. Thanks for inviting me. I'm very happy to be back. I had to skip the last event last year, so I'm really happy to be back in Pisa. Yes, the title. So this is a very much ongoing work with Jason Smith, who is there. And so yesterday, I think we had a talk about 25 years old project. This is less than 25 weeks old project. So it is very much ongoing. So I think there's more questions and answers here. I don't know. There was some special session yesterday. I don't know. All right. So I had the magnificent idea of outlining or justifying my talk by the conference title, and we already saw it yesterday happening. So anyway, this is my outline. So combinatorics. So I'll be talking about sandpile dynamics, or also called chip firing games on digraphs. So this is very much a topic in combinatorics. So we have C. Then topology. So we will be constructing this avalanche complex and then the homology of sandpile. So we have topology, and there was also some application sort of background. So there's a picture from this paper where actually Ran is one of the authors as well. So what they were doing, this paper, they were looking at these quite large directed graphs coming from a network of brain neurons, and they were simulating brain activity on this network. So this is this time evolution of these active regions, these red regions in this network. And then they look at the homology of the directed, so-called directed flag complex of these active subnetworks. And they look at Petty 1 and Petty 3, so the first and third homology. And this is the plot, I think, Petty 3 versus Petty 1 versus Petty 3. And the Petty numbers fall into this quite intriguing sort of dynamic trajectory over time, which is something you wouldn't expect a priori. I mean, the Petty numbers could be scattered however. So somehow the homology falls into this quite constrained trajectory. So I've been interested in these kind of questions for, since my time in Aberdeen. And we're doing this computational with Jason at the moment, using the sandpile dynamics on big collection of different digraphs and trying to see if the homologies are somehow connected to some dynamical measurements of networks. So while doing this, then this led to thinking that what would be a homology theory for sandpiles, and then we came up with avalanche complex and avalanche homology of sandpiles, and this is going to be the topic of the day. So what is the sandpile model, or also called chip firing? So we start from a graph G. G will always be a generic graph on n vertices. And then the sandpile model on G is this kind of dynamical system. So we have a some configuration on z to the n at time t, and this is the elements of this vector are representing a pile of sand on each of the vertices. So if you have some element, let's say 5 on the vector, it means that the corresponding vertex will have a like pile of 5 grains of sand on the vertex. And then a vertex is ready to fire if the corresponding element in that vector is larger than the degree of the vertex. And then firing a vertex adds 1 grain of sand to each of the neighbors of that vertex and then subtracts the corresponding amount of vertices, so degree of v grains from the value at v. And then this process repeats over steps where you always choose a vertex that is ready to fire and you fire it. This one? So the CT, this is just a configuration vector at some time t in z to the n. Then you look at the vth element of that vector corresponding to the vertex v, and you look at if that element is larger than or equal to the degree of v. Not in this model. There is something called a dollar game, where you can have negative values because the vertices can have a depth. But in the sandpile model, you want to look at legal configuration, so everything is positive. But there are variations where it can be also negative. So you can think about it, instead of z to the n, you can put just n to the n. So yeah. And then with a configuration stable, if all the elements of the configuration are less than the corresponding degree, than the degree of the corresponding vertices. No shootings, no firings. That's more like let's not shoot anyone. And then there can be variations. There can be a chosen sink vertex in the graph, such that there is a path from any other vertex to the sink. And sink is something that never fires. So everything that falls into sink just stays in the sink. So it's a kind of absorbing vertex. And now this model gives rise to this dynamical system on a graph that is governed by the graph Laplacian. So just remind you or introduce if you don't know. So the graph Laplacian is this matrix where well, A is just the adjacency matrix of your graph, and D is a diagonal matrix where on the diagonal you put the degrees of all the vertices. So now going from a configuration at time t to time t plus 1 by firing a vertex vi is given this way. So we subtract from the configuration at time t, we subtract the ith column of the Laplacian matrix. Well, so we multiply by the ith standard basis vector that just have value 1 in position I and everything is 0. So here's an example how this works. So we start from this configuration, and now we fire 2. So we see that the value of the configuration at this vertex is at least the degree of the vertex. So this one fires, and it sends 1 chip to both of these neighbors. So this was 0, so each of them gets 1 chip or grain of sand from this vertex. And then this becomes 0 because we subtract the 2 from that vertex. And now this vertex is ready to fire, so we fire it. It sends chips to its neighbors. So this becomes 2 then, and this goes down by 2, so it goes 2, and so on. And so on, the process continues by choosing always a vertex. And at this point, we see that, look, this is a configuration that is exactly the same here. So we have reached our goal recurrent configuration. And now if we continue firing from this configuration, then we get back to something that we already see that should be coming next to this configuration. So from this point on, the dynamics is recurrent. So it just repeats the same orbit. It is ready to fire, but we just choose this to fire first. No, so there's a basic fact of sandpile model. This is called abelian. So that's why it's often called a abelian sandpile model. So the order of vertex firings doesn't matter. So you can choose any vertex that is ready to fire, and it will end in essentially the same result. That's it here. It's also called confluence property or like a diamond property. There's a much more formal statement, but it's essentially this is what we need. So it is abelian. It comes from like late 80s in physicists like Buck, Tang, and Wiesenfeld model. They were studying the self-organized criticality in statistical physics. So systems that without any output forcing somehow find their way into some critical states. So this was an early example, and then a couple of years later, Dar was studying this abelian version of it. So it then gave rise to the abelian sandpile model, and then rest is history. There's another famous combinatorial fact. So the number of spanning trees of your graph is the same as the number of recurrent configuration of the sandpile model. And it's also the same as the number of so-called critical configuration of the model, where a critical configuration is something that is it's a stable configuration, and it's a configuration that is reachable from some starting configuration where every non-sync vertex is ready to fire. So it's sort of a large enough configuration that everything is about to fire. So that's a critical configuration. And there's something that is very important. There's an algebraic invariant of graphs, so-called sandpile group. So we have a graph with a sync vertex. We have the sandpile group, which is a finite abelian group on the set of recurrent configuration, where the addition is so-called sandpile sum. So it's just the normal addition of this configuration vectors followed by stabilizing these configurations. And that is a very important topic also in sandpiles. All right, so these are just like I'll give you an idea of the basic facts or the basic mathematics behind the sandpiles. I'll give you more connections as we progress. And this is, I think, cool. So sandpiles give rise to this fractal pattern formation. So here we have the grid graph on Z2, and you put 20 million chips at the origin, and then it just start the model, and it gives rise to this cool fractal kind of configurations. I think so. I think red means that there are 3 chips on these vertices, and yellow is 2 chips, and so on. So you get this kind of pattern. So here's another pattern. So this is so you have a 1000 by 1000 grid graph, and all the boundaries are connected to a sink. So think about this like a tabletop where you start pouring sugar on, and everything that reaches the boundary of the table just falls to the floor, and it gives rise to this kind of pattern. And this is actually the identity element of the sandpile group on this 1000 by 1000 grid graph. And these patterns are sort of open mathematical questions. We know very little of how these patterns come about, and these take you into PDEs and Apollonian circle packings and all weird kinds of mathematics that's like completely disconnected from the topic of this conference. But there's a cool mathematics behind. And one open question, for example, is that this constant region of 2 chips in the identity element. There's just conjectures, but no one knows the answer of why this is there. All right, so this is just the flavors of the sandpile and mathematics behind it. We want to go to digraphs. So now we fix G to be a generic digraph on n vertices. The sandpile dynamics is just as before. Only thing it changes is that now the vertex V is ready to fire if the configuration, if the corresponding element, the configuration vector is larger than or equal to out degree, not the degree, but out degree. And firing V adds 1 grain of sand to each of the out neighbors, and then subtract the out degree V grains from V. So that's the only thing that changes. All right, again, a little bit of like wider context of connections to other mathematics. So there was a quite intriguing paper a couple of years ago coming from Levitt path algebras. I don't define Levitt path algebras, but it's just a kind of path algebra that you can connect to directed graph. It's a graphical discrete version of C-star algebras. So let's just write this V of A to be the monoid of the isomorphism classes finally generated projective A modules over the ring A. So they wrote down this kind of theorem. So let's E be a digraph with a unique sink, such that from every vertex there's a directed path to the sink. So this is called like a sandpile graph. This SPE to be the associated sandpile monoid, not the group, but just the monoid of the configurations, and then K a field. So they proved that the sandpile monoid is actually isomorphic to this monoid of the isomorphism classes of the projective modules over the Levitt path algebra on certain graph E that comes from this, E prime that comes from E. It's a vertex weighted digraph obtained from E for a certain sort of quotient construction and so on. And moreover, then the sandpile group of E is isomorphic to the Grothendieck group of the modules over the Levitt path algebra. So very intriguing connections to like beginning of the K theory of this Levitt path algebras. There are some technical details are brushed off, but essentially this is what they wrote. So I think it's demonstrating again that the sandpile model somehow connects to various things in mathematics. No, so this is all in this paper that they did. I don't know if there's any continuation going on, but so yeah. Sorry? Well, not something I can recite here now, but you essentially start from a graph. Then for every edge, you also add kind of like so every edge E, you add another edge E star, which is sort of like a opposite of E, and then these have to satisfy a bunch of relations. So kind of like modeling the C-star algebra, so on the edges and vertices. Yeah, that's all I will say now. Right. So moving on towards what we want to talk about, so the avalanche, complex avalanche homology, avalanche dynamics. So instead of firing a single vertex at a time, we are more interested in avalanches. So we take the sigma t to be the subset of the vertices that are ready to fire at a time t, and then we just fire all those vertices simultaneously. So we instead of firing single vertices, we take avalanche of this subset of vertices. And then the avalanche of this set sigma t is given like before. So going from time t to time t plus 1, we subtract this multiplication of now the directed graph Laplacian with this. This is just the indicator vector. So it's just the sum of the basis vectors that correspond to vertices in this set, this avalanching set sigma t. This transpose is here important because now with directed case, this Laplacian is not anymore a symmetric matrix. But there's a simple description of this dynamics. One thing to note that we do not consider sinks, so vertices that have outdegreed 0, to belong to avalanches. So those are left out. So we don't consider that the sinks are avalanching. So now we can define the avalanche dynamics on G with some initial configuration C0 as the sequence of pairs. So configuration at time t, and then the subset of vertices that is about to avalanche. And this is your dynamics going from a configuration to another by avalanching this subsets of vertices. And I will abuse notation sometimes by denoting the sigma belonging into this dynamics to mean that the set of vertices sigma avalanches at some time step t, such as this sigma appears in some of the pairs. And I also sometimes just drop the initial configuration when there's no need to specify the initial configuration. All right, so that's the avalanche dynamics. All clear? All right. And now, if a subset avalanches, then any subset also avalanches. So there's a clear simplicial condition satisfied. So now, simply the definition, the avalanche complex of your digraph with respect to some initial configuration, this is generated by the maximal, with respect to inclusion, avalanching sets in your dynamics. So the biggest avalanching subsets in the dynamics are the maximal simplices, and then you just generate the simplicial complex from that. Sorry? So avalanching set is just subset of vertices such that every vertex in this subset is ready to fire. So each of these vertices will have value in the configuration larger than their out degree. Yeah. And then avalanche homology is just the simplicial homology of the avalanche complex. Very straightforward. It's a max. Well, yeah, you should. Well, so we just take the largest sets that are avalanching during the dynamics. Yeah, and if there's a smaller subset, well, then it's anyway a bigger, large inside the larger avalanching set. So. It's throughout the dynamics. Yes. All right. Okay. So this is the basic definitions. At this point, I'll again want to draw some connections to wider context of things. So there's again very, very recent work, so-called burning homology. There are bath homology people here, so you probably know this guy from bath homology. So they were looking at this graph burning. It's another discrete time process, this discrete dynamical system on graph, where each vertex is now, each vertex is either burned or unburned. So all these dynamical systems are very violent. So we talk about firings and burnings. Like, oh. So at every round, we choose an unburned vertex to burn. So this is so-called burning source, if there is such a vertex available. Once a vertex is burned at some time t, then at the next time step, its unburned neighbors are burned. So the burning begins to spread from the burning source. If a vertex is burned, it remains burned until infinity. And then the process ends when all the vertices are burned. So I just want to burn through the whole graph. So they describe the burning of a graph G. These are graphs, not digraphs. The burning of a graph by this pair, where this SG, this is just a sequence of burning sources. So these are the vertices that we incrementally at every step choose to burn. And then there's this function on the vertices that just maps a vertex to the smallest I, such that the vertex appears in this induced subgraph. So what is this? This is an induced subgraph induced by the vertices which are in the burned state at time t, including the source that we burned at time e. So what this is keeping track of this function is just the when is the first time that a vertex becomes burned. So this is all then you need to describe this burning process on a graph. And for any finite graph, there's just a finite number of burnings you can perform. So every source sequence here, just forget about the ordering of the burning sources, it just yields a subset of vertices, and they very similarly they define the burning configuration space to be the simplicial complex on the vertices that are generated by these burning source sets. And then the burning homology of a graph is the homology of this simplicial complex. So very, very similar kind of thing. I'll get back to some examples to compare with the avalanche homology later on. But just to like draw again connections to what's happening around. All right, so back to avalanche homology. So let's denote the size of the sandpile or the size of the dynamics. This is to mean the total number of chips in the dynamics. So it's just the sum of all the elements in the first initial configuration vector. So here's some first simple results. Of course, if the full vertex set belongs in the dynamics, so at some point the full vertex set avalanches, then your avalanche complex is just the full simplex on V. So we get that the complex is contractible, and it follows that for any cycle on n vertices, if the size of the dynamics is at least n, then the full set of vertices will belong into the dynamics, and any cycle is contractible in this case. This just follows the very generic logic behind proving things on the cycles, that any configuration you start from in a cycle, when you start doing the avalanche dynamics, at the end of the day, at some point, it will stabilize or find a configuration that is just zeros and ones. And because every vertex in the cycle has out degree 1, anything that has 1 will always fire, sending the chip downwards. So you just end up on a configuration of zeros and 1 that just rotates around the cycle. And if every position on the cycle is filled, all the vertices fire at every step. So the full vertex set is in the dynamics and it's contractible. So that's something we know about cycles. Now you might ask that, is it generically true that if the size of the dynamics is at least the size of the vertices of your graph, is the avalanche complex is always contractible? Well, of course not. It depends on the graph. So here we have 4 vertices, but 5. The size of the dynamics is 5, so we have 5 initial chips on this vertex. So if we run the avalanching process, then first A avalanches singly. It sends 1 chip to B, 1 chip to C, and now we see B has 1 chip. It has out degree 1, so B avalanches. A still has 3, so it also avalanches. So now AB avalanches, and so on. And after this, it stabilizes. And what we see as simplices here, we have AB, BC, AC, so we have the boundary of 2 simplex. So the avalanche complex is, in this case, is homotopy equivalent to S1. So not contractible. So now the next question we've been interested in is, what is the extent of avalanche homologies we might see for different digraphs? So let's look at an example again, or a path on 6 vertices with such an given initial configuration. So the maximal simplices in this case are T's. I drew the simplicial complex illustrated here. So this is just homotopy equivalent to the triple wedge of S1s. So we get this kind of homologies. Some kind of results about paths. So for paths of length larger than 4, note that because we don't consider the sinks to be in avalanches, then n doesn't include the sink vertex. So this is like actually a path of 5 vertices, but we don't include the last one. We treat it as a sink. And this is the initial configuration. So 0, 0, 1, 0, and then everything else is zeros. So now we know the first Petty number. In this case, it's n minus 3. Petty 0 is 1, and everything higher vanishes. So there's something we can prove about paths. So now the comparison to burning homology that I promised. So they look at, in the paper, they look at paths for up to 6 vertices and their burning homologies. These are all the non-trivial burning homologies that you get for paths. So you have nothing more than H zeros. There's H1, H1 happening here, but otherwise there's nothing more non-trivial essentially than H zeros. I'm the kind of person who likes to see a lot of homology, so I think this is kind of poor. So I think this is more cooler, that there's like bigger homologies here. Okay, so let's see, just computationally, let's explore like what's the extent of homologies. Everything is over field F2. These were actually over Z, but for computations, we are doing over F2. So now we look at the pad on 6 vertices, and I put 6 chips on the vertices, and like all the configuration that have size 6. And these are the Petty numbers that we see. So there's some Petty 1 and Petty 2. 36 of these are homology spheres, so I have the Petty numbers of some sphere. Quite a big chunk of them are trivial, so meaning that there's just Petty 0 equals 1. So there's nothing more. There's no homology more than 2 degrees. Same happens if we put 7 chips on the vertices. These are the number of configuration. We get some Petty 3. Again, some homology spheres. Most of them are homology trivials, and no homology more than 2 degrees. Right? So that's some paths. Okay, let's see. Then cycles. I think these are a bit more interesting. So this is something that we know for a cycle. Again, so now at least the number of vertices at least 3. And for this kind of configurations, where the size of the dynamics is n minus 1, so we have n cycle, and we put n minus 1 chips on the cycle. Then for any initial configuration, the avalanche complex is homotopy equivalent to the Sn minus 2. Again, the logic is similar, that you have this n minus 1 chips rotating around n vertices. And here's a good helpful theorem for cycles. So if we have any non-binary configuration, meaning that for some element of the configuration vector, it's larger than 1, so it's not just zeros and ones, then there is a binary configuration such that your avalanche complex on C is homotopy equivalent to the avalanche complex on the C hat, this binary configuration you get. Again, the cycle has the process of sort of stabilizing everything to just the 0 and 1 configurations. So with this theorem, you can compute a lot of things for cycles. So here's an experiment on cycles on 10 vertices with size of the avalanche being 5, so 5 chips. This is the number of different configuration we need to look at. And here are the Petty numbers we get. All right, so Petty 2, Petty 3. There's much more Petty 2s than number of configurations. So there's some kind of homological wedges of Petty 2s. 6 of them are homology spheres. And now we actually see homology more than 2 degrees, which is makes me happy. Similarly, okay, let's put 6 chips. We get this kind of pattern. Let's put 20 vertices on a cycle, 7 chips distributed. This is the number of configuration we need to look at. And these are the Petty numbers we get. So we get 2, 3, 4, huge amount of almost 3 million Petty 2s. get homology spheres, and we get a lot of also homologies that are in more than 2 degrees. So there is a potential of creating different kinds of homological types. So now this is one question that has no answer, but that I'm interested in. So if I'm given any space and its Betti numbers, is it possible to find a construction that gives me some digraph G and some initial configuration on it, such that the Betti numbers of the avalanche complex will agree with the Betti numbers of the space? So can I realize the homology of any space with this dynamical process? I don't know. Sorry? Well, just numbers. Yeah, sure. But I mean, well, it's cooler because this is a topology conference to have a space that has Betti numbers than just numbers. So you get a space, sure, you get a space. Yes, okay. And I see the point. Okay, so this is actually a trivial question. So it's realized by the space itself. Okay. All right. Well, okay, maybe this is more interesting. These computations that I showed, these were over field coefficients. Can we realize any torsion on the avalanche complex? I don't know. Okay, well, I put it very small because I don't like to say anything homotopical, but it's any homotopy type of spaces. But, well, yes. So the avalanche complex itself satisfies this. But maybe the more question is this, maybe the more interesting question is that, is there some obstruction that this dynamics cannot attain some Betti numbers? So somewhat related we are working on is to look at how these configuration spaces, different graphs, decompose. So we know that this is for a cycles Zn. This is now the configuration space Zn. You have to just think about it's like projected on this two-dimensional picture. We know that, okay, this configuration 1, 1, 1, 1, 1, 1, 1, everything beyond that is contractible by the result we had. We know that these projections to the coordinate axis, so this has n-1 chips on the vertices. We know that these were the Sn-2s. What happens here? Are they all the homologies? Are they all point-wise all different? Is there maybe some kind of regions of constant homologies? So these are, we have some partial results of certain cases, but can we prove this in the full generality? I don't know. So this is sort of the tentative theorem that the avalanche homology of Cn decomposes the configuration space into some kind of regions. Can we do the same for paths, which are also very simple digraphs? Even the configuration, the initial configuration such that this complex is contractible are a bit more difficult to characterize than for cycles, because for cycles we knew that as long as the size of the configuration is at least n, it's contractible. And then for some other classes of digraphs, can we do the same? Probably very, very difficult. Maybe in some very restricted classes of digraphs, but I don't know. And that's all I wanted to say. And I finished in, well, very much in good time.
Okay, thanks. Questions? Well, we did ask some questions already, but other questions?
So you said that some of the examples, for instance, you referred to what you get as homology spheres. Can you say something about the fundamental group of the resulting spaces?
Not at this point. So this is essentially where we are now. So some results on the homologies of cycles related to this decomposition theorem, and then experimental, like what are the homologies we see, like these computations, but
So I assume the computations were done mostly by machine, right? Not by hand.
yes, I didn't compute 77,000.
Exactly. That's what I thought so. I mean, I know you, but you know, even you will not do that. Do you have any indication that whether or not, or kind of conjecture, that some of these Betty numbers are basically just wedges of spheres, or do you think it's something more like a richer structure?
I don't know. So we look at also a wedge of two cycles.
Mhm.
And then if we put like non-symmetric configuration of two cycles, so then you start the dynamics. So it's sort of like a bit more chaotic dynamics. And in these cases, you might be able to produce more richer Petty numbers, homologies, but don't know.
I have two questions. Both may be silly. Do you have any kind of Maya-Vistris arguments for your avalanche complex?
No.
No. Right. Under any condition?
No.
No.
Something
Okay.
haven't been looked at all.
All right. All right. The second question is that does it make sense to consider the minimal number n such that your graph G is covered by n elements of SP of G?
So repeat again. So minimal number of n.
Minimal number n,
Yes.
such that your graph G is covered by n elements of SP of G,
All right.
a kind of LS typing.
Yeah. Yeah. I haven't thought about it at all, but yeah. I think it sounds reasonable to me. Yeah. Yeah.
Okay. Thank you.
We can talk more also. Like,
Yeah.
So do you have any idea or indication if this avalanche homology can classify directed graphs, maybe with some chips, like if the graph is a directed cycles with this number of chips, then the Betty numbers are going to look like that. If it's a path, they're going to look like something else.
well, I think sounds to me basically like this decomposition theorem that like what are all the Betty numbers or homologies for all the different configurations? Or
Right, but is okay. Yeah, maybe I was. I mean, is that telling you something more about the like original structure of the graph? Some.
maybe not.
Okay, yeah.
Yeah. Like I said, I have more questions than answers.
So this is a bit of a continuation to the commutativity question I asked before. So so if the chip firing is commutative, in a sense that if you allow for depth, right? So if you start with a configuration, then it doesn't matter which order you shoot each chip, right? You will shoot, let's say the process is finite, so at some point it will stop. Couldn't you just reorder everything and just look at the numbers of chips fired from each vertex?
I'm sure I understand what you're asking. Just a reorder or reorder
that's commutativity.
Names of the vertices? Or?
Yeah. No, well, I can show it later. It's fine.
Okay.
Okay, well, I think we had enough questions, so let's thank Henri again.
Okay, good afternoon, everyone. Welcome back. Hope everyone had a very nice one. This afternoon, we've got Bailey Shooter from the University of Aberdeen, who's going to be talking about real and complex line fields on manifolds.
Thank you so much. I just want to thank the organizers for putting on such a lovely and friendly event. I'm really excited to talk because 2 weeks ago, I finally submitted my PhD thesis. So I feel like I can, celebrate by, thank you, by giving everyone like an overview of what I've done during my PhD. The real part of this talk is joint with my advisor, Mark Grant, and the complex part is joint with Nikola Sadovek, who talked last year at this event. So some of you might know him. He, I think, is still at FU Berlin, but he's moving to Dresden. I'm not sure if he's there already now. Okay, this is my kata thing. I've got the algebraic topology part down in this talk. I also have like some attempt at applications. You'll see what I mean. I think what I'm missing is the combinatorics. I don't really have any combinatorial stuff. I've got some CW complexes, so that's about, I don't know if you can even call that combinatorial, but what I want to talk about, there's sort of 3 parts to the talk. The first part, I realize that maybe not everyone cares about manifolds and definitely not about line fields on manifolds. So I'll try to give you some reasons why you might be interested in these things. And also there's kind of one main result that I want to communicate today in this talk. And I'll give you a very vague statement of it at the beginning, and then I'll try and make that statement less vague by the end. The second part is going to be dedicated to the first half of my thesis, which is about the line bundle decomposition problem 1, is what I'm calling it. Not very much is known about this problem, so I can sort of catch you up on literally everything that we know. And I'm hoping the second part will be the fun part of the talk, where I can kind of give you a lot of interesting examples, and I won't really go into proofs or the methods used. And the second, or the last part of the talk, the third part, is where the main theorem will be. And this is about the line bundle decomposition problem 2, which is a variant of the first problem. And I'll say something about the very small contribution of the second part of my thesis towards this problem. So this is the outline. So to begin, we're starting very roughly. I'm just going to focus on manifolds for a minute. So say we have a smooth closed connected manifold M. A vector field, let's recall, is a smooth section of the tangent bundle. And what does that mean? That means to every point on the manifold, we assign in a continuous and smooth way a tangent vector at that point on the manifold. A line field, on the other hand, you can say that it's a smooth section of the projectivized tangent bundle. So the projectivized tangent bundle is a smooth fiber bundle, and the fiber is real projective space. But I mean, you can just think of it, at each point on the manifold, you're smoothly and continuously assigning a tangent line at each point on the manifold. Okay, now every vector field gives you a line field. So we can just kind of think very roughly about this. So if you have a vector field, at each point you've got a tangent vector. This vector spans a tangent line, so that will give you a line field. But not every line field comes from a vector field, and that's kind of the point. Maybe I can just quickly, don't know if everyone can see this, just maybe draw you a very quick example. There's a lot of fun examples, but maybe I'm very bad at drawing. Let's look at a torus. This is a line field on a torus that doesn't come from a vector field. Maybe it's better if I draw it like that. I don't know. I'm sorry, I'm so bad at drawing. So it kind of looks something like that. Maybe you can see how if you start adding arrows, like if we add an arrow like this, if you kind of fill in this picture, you're going to get an arrow going like that. And then you're going to have some problem when you get on this line here. See what I mean? So there's going to be 2 vectors pointing in opposite directions when you get to the line. So anyway, the point is this is a perfectly good line field on the torus, but it's a bad vector field. It's not a well-defined vector field, because at some points you'll have 2 different tangent vectors assigned to each point. Okay. Now, so I want to say why study line fields? I don't know. Sometimes Well, okay. Maybe everyone can sort of jive with the classification problem. We want to classify smooth manifolds up to diffeomorphism. And the process of diffeomorphing your manifold can distort things like curvatures and volumes, but line fields are really good because they're preserved by diffeomorphisms. So, for example, the maximal number of pointwise linearly independent line fields on your manifold, that's a diffeomorphism invariant. It really does depend on the smooth structure. And theoretically speaking, you could distinguish smooth structures using projective span, which is the maximal number of linearly independent line fields on your manifold. Unfortunately, this is very, very hard to compute invariant, and so it's not really a practical strategy. But I don't know, just if we're thinking idealistically, that's some kind of motivation. And this is my attempt at applied motivation. So let's see if you feel convinced. Okay, so in soft matter physics and also synthetic chemistry, I've seen many examples of these kind of people using line fields to model these nematic liquid crystals. Now, I don't really know what these things are. They're kind of like halfway between a solid and a liquid. I don't know anything about physics, but they're sort of ordered media made up of these little rod-shaped particles, and they have like an axis of alignment, but it doesn't really, they don't have a preferred axial direction. So that's why you can use lines to model them. And they sort of stack together. They kind of align with each other in the stackings and create these weird textures. Now, biaxial nematics is some kind of catch-all phrase in physics to refer to this kind of ordered media that has more than one axis of alignment, like 2 or 3 or 4 or 5. And it's sort of like a holy grail, it seems, in soft matter physics, the synthesis of the biaxial nematic phase, because it's supposed to have important applications to display technology. There's some people in Aberdeen who are trying to build this like self-focusing contact lens, and I've had some interesting discussions with them. But anyway, so you can use tuples of linearly independent line fields, which is what I'm interested in, to model these things, maybe. I don't really mean to suggest that my research actually could contribute to this kind of thing in any way, but the theorems, especially the one at the end, they improve our understanding of the topological obstructions to the existence of linearly independent line fields on manifolds, and that could lead to a deeper understanding of these soft matter defects. This is a picture I found on the internet of, this is a uniaxial nematic liquid crystal. So I don't know, you get these kind of funny textures, and you can kind of imagine how you could use a line field to model this somehow. I don't know, pretty picture. Okay. Sorry, no, okay. So now I want to state the main theorem in this vague way, and I want to kind of compare it to a theorem that hopefully everyone's seen before. So maybe everyone's heard of the Henri-Ball theorem or the hedgehog theorem or whatever, which says that a two-sphere doesn't have a non-vanishing vector field. This is a very, very old theorem. Hopf's theorem is a bit stronger than this. It says that your manifold admits a non-vanishing vector field if and only if the Euler characteristic vanishes. This theorem is over 100 years old. It's this really, really nice theorem where you have this algebraic or numerical invariant, and the behavior of that invariant totally governs this geometric phenomena. So it's just a really, really nice theorem. And our main theorem has the same form as this. So it has this flavor of this algebra thing governing this geometric phenomena that we want. So Nicola and I have this sort of theorem. So we want to say that for certain almost complex manifolds that have certain properties, we can say that they admit 1, 2, or 3 linearly independent complex line fields if and only if certain characteristic classes of these manifolds vanish. And I just want to fill in the details of this theorem. Okay, and now this is the end of the first part of the talk. I just want to make some real definitions now. So for the rest of the talk, this blackboard face F will be either the real numbers or the complex numbers. I can't quite do the quaternions yet because of horrible complications. And V will always be an F vector bundle, so either a real or complex vector bundle. And X will usually be a CW complex, but for now, it can just be a topological space. So V is a vector bundle over X. And the span of V, or the F span of V, is the maximal number K, such that V admits a rank K trivial subbundle. So this F underlined to the K is my notation for a trivial subbundle, or a trivial bundle of rank K over X. In the language of sections, if the span of V is equal to K, that means that there exists K linearly independent sections of this vector bundle V. And if V is the tangent bundle of a manifold, the span of the tangent bundle tells you the maximal number of linearly independent vector fields on that manifold. Is everyone happy with this? And the projective span is kind of a weakening of this. So if you have a rank K trivial subbundle, that trivial bundle will decompose into the K-fold sum of trivial line bundles. And you can ask, well, what if I let the line bundles be possibly non-trivial? So that's what the projective span is. The projective span of this vector bundle V is the maximal K such that there exists K line bundles whose direct sum splits off V. And again, if V is the tangent bundle of a manifold, the projective span of the tangent bundle tells you the maximal number of linearly independent line fields on the manifold. Okay. Any questions about these definitions? I will say span and projective span a lot of times. Okay, and maybe this is clear to you, maybe it isn't, but if you have a given vector bundle, the span is bounded above by the projective span, and the projective span can't possibly be more than the rank of the bundle. And you might be worried about the strictness of the middle inequality. The span and projective span can be very different from each other, and we'll see many examples of that as we go on. Okay, this is part 1 of the talk concluded so far. We've had some, hopefully not too BS motivation, and we defined span and projective span, which is the important thing. And now I want to tell you about the line bundle decomposition problem, which is really the topic of the first half of my PhD thesis. So we have some F vector bundle over a CW complex, and the problem is compute its projective span. That's the problem. And I said this in words before, but if M is a manifold and V is the tangent bundle of this manifold, you might shorten notation and call the projective span of M to be the projective span of the tangent bundle. And in this situation, the determination of the projective span of a manifold or a family of manifolds, we call that the line field problem. So it's just a nicer name than line bundle decomposition problem 1. I guess I'm back to trying to motivate this in terms of classification, but you could view this solutions to this problem 1, as a partial step towards the classification of vector bundles, whether or not you care about vector bundles. I mean, if the line bundles that you're trying to split off all happen to be trivial, then you're sort of asking, how far away from being trivial is my vector bundle? And just as some example solutions to problem 1, you could look at complex rank 2 bundles over complex 2 manifolds. Those things are totally classified by their first and second Chern classes. So if you know the first and second Chern class, you can work out whether or not it decomposes into 1 or 2 complex line bundles and get a solution to problem 1. If you go just one step beyond this, you might have heard of this famous kind of story. So if you look at rank 2 complex bundles over CP3, these things are no longer classified by their characteristic classes. And there's this really amazing paper of Attia and Rees where they completely classify these bundles, some really impressive work. So this gives you a very, very non-trivial but complete solution to problem 1. I don't know, probably no one cares about algebraic vector bundles in this room, but Grothendieck famously proved that every algebraic vector bundle over CP1 decomposes totally into lines. So this is also like an interesting problem in that kind of world. Yeah. Yeah, I mean, I guess it's other kinds of cohomological data. Maybe you can't call it a characteristic class. Yeah. Yeah, that's a very interesting question. Sort of, yeah. It's a computable invariant, but maybe not a characteristic class. Okay, so here I've just restated problem 1 in case you forgot it. So we have some vector bundle. We're trying to compute its projective span. This is a really, really difficult problem. It's easier than the classification of vector bundles, but it's just virtually wide open. It's a very hard problem because there's really no widely tractable strategy. The method of attack, the strategy you use is just totally dependent on the specific vector bundle that you're looking at. Maybe you have success in some situation and you try and generalize it to other situations or move it around or modify it in some way. But to be honest, it really doesn't happen a lot. You won't get lucky, and this problem is just wide open. So I want to tell you about everything we know really about this line bundle decomposition problem. But before I do that, I'm just going to tell you about the span version of this problem, which is the more well-studied version. So if I get rid of p-span in this problem and I replace it with span, so I'm just trying to compute the span of a vector bundle, we know a lot more. And just as a warm-up, I'll tell you a few things. So maybe everybody has seen this at some point. If you have a Lie group, Lie groups are parallelizable, which is a great thing. And by parallelizable, I just mean that the tangent bundle of the Lie group is trivial. So the span of any Lie group is equal to the dimension of the Lie group. And you can use this to figure out whether or not a space has the chance of having a Lie group structure. So for example, you might ask which spheres can be Lie groups. Well, only the parallelizable spheres have a chance at having a Lie group structure, for example. Speaking of spheres, there's this very famous computation of the span of spheres. In the 1920s, early 1920s, Radon and Hurwitz were two algebraists who independently gave a lower bound for the span of spheres. So they said that there exist a certain number of vector fields, linearly independent vector fields on spheres, and they used very elementary methods to prove this. This rho m semicolon r is called the Radon-Hurwitz number, and I won't define it, but it will come up later in the talk. We'll have other Radon-Hurwitz like numbers, but many decades later, it was Adams who, as one of the first great successes of generalized cohomology theories, he used his Adams operations in topological K-theory to show that the lower bound for the span of spheres given by Radon and Hurwitz was actually the upper bound. So he finished this span computation. But this was many decades of work, and there were lots of papers in the interim kind of getting close, but not really finishing things up. Okay, so we know the span of spheres. And then the next sort of famous thing that happened is this work of Radon and Kaczynski, which maybe you've heard of it. They proved this interesting conjecture called the Eagle conjecture for stably parallelizable manifolds. And they really generalized what Adams did because spheres are stably parallelizable. And by stably parallelizable, I don't want to get into the stable part of this problem too much. I just mean that the tangent bundle plus a trivial line bundle is trivial. That's what it means to be stably parallelizable. So it's not parallelizable, but the stabilized tangent bundle is trivial. So this is the Eagle conjecture. It's often not referred to as the Eagle conjecture. I learned to call it the Eagle conjecture from Dermot Crowley, who learned to call it that from Svengrowski. And I think Svengrowski learned to call it that from Koshorka. So that is the lineage of the name of this conjecture. That is not written down anywhere. But here, so we have a smooth manifold, and it's m-dimensional. The conjecture is that the span is one of two things. Either its span is the same as the sphere of the same dimension, which we've seen the computation of, or it's the same as the stable span of the manifold. And I didn't define the stable span, but the stable span is the span of the stabilized tangent bundle minus 1. That's what it is. So what's really weird is a lot of manifolds satisfy this conjecture, or we don't know enough about the span of the manifold to be able to show that it doesn't satisfy this conjecture. As far as I know, and there's so much literature, I have only found counterexamples in Kashorka's really weird monograph. He has this book about vector bundle monomorphisms, and he develops this kind of really interesting cobordism theory stuff. But he gives some counterexamples to this conjecture, some very meaningful counterexamples, and I can't find any anywhere else. Yes, so Bredon and Kuczynski proved this conjecture for the stably parallelizable manifolds. So we know it's true for them. And it's, for small m. Oh, so you want like low dimensional manifolds. Well, this question isn't that interesting for low dimensional manifolds because like the span is really easy to compute for surfaces. So I think they satisfy this conjecture. And then for 3-dimensional manifolds, orientable 3 manifolds are all parallelizable, for example. I don't know about non-orientable ones, but yeah. So this is like a high dimensional manifold question. Okay, so I just wanted to give you like a bit of the like super highlights of the span version of the line bundle decomposition problem 1. Now I can finally tell you the stuff that we know about computing the projective span of manifolds. There's the Klein bottle, which is a nice example, and it's actually a pretty important example that's very helpful. So I want to try and convince you that the span of the Klein bottle is 1. So it emits 1 non-vanishing vector field and no others, but its projective span is 2. So the projective span is strictly bigger. So the way that we want to prove this is by viewing the Klein bottle as a mapping torus. So I'll take a circle and cross it with the interval and get this cylinder. This cylinder is parallelizable. It emits 2 linearly independent vector fields. And I've drawn them, the vertical one is in orange here, and I've drawn the orthogonal purple one. So hopefully you agree that the span of this cylinder is 2. I want to convince you that the orange one, when we take the quotient and build the Klein bottle, that one will still descend to a well-defined vector field on the Klein bottle, but the purple one will become a line field when we build the Klein bottle. So the way that we get the Klein bottle from this cylinder, we want to glue the 2 ends of the cylinder along a twist, and the twist that we pick is a reflection in 1 coordinate of the circle, where I'm viewing the circle inside of R2. It doesn't matter what coordinate, but this gray line that I've drawn here is supposed to be the axis of reflection defined by this rho. So I hope that makes sense. So to build the Klein bottle as this mapping torus, we've built the cylinder, and we're going to glue the 2 circles on the boundary of the cylinder together using this homeomorphism of the circle defined by this reflection. And the vertical vector field, this orange one, it's going to be completely fine when we do this gluing. It's just going to become a vector field. Hopefully you can imagine this. But it's the purple one that's going to cause a problem. So I'll just try and quickly convince you of that. So you have this horizontal purple vector field. And let's look at this point X on the axis of reflection, just to be easy. So this X on the top of the cylinder, it's going to get glued to its image under the reflection map rho, but we're on the axis of reflection. So rho X is just equal to X. So it's just going to get glued to itself on the bottom. And you can differentiate this rho. And so if this purple tangent vector is the vector defined by this purple vector field assigned to X, you can calculate that the differential of rho is going to flip that tangent vector. So maybe just believe me about that. And that's what the problem is. So when we carry out the gluing, X and rho X are going to have 2 different tangent vectors pointing in opposite directions. And that's not a well-defined vector field anymore. But it's a perfectly good line field because they live on the same tangent line. So we get a nice line. And the last thing to finish up this computation is the span of the Klein bottle can't be 2. If it was 2, that would mean that the Klein bottle is parallelizable. And that would mean that the first Stiefel-Whitney class is 0, for example, which contradicts the fact that the Klein bottle is non-orientable. So we can't have the span any bigger than 1. Okay. Any worries about that? Okay, that was the first span, projective span computation. So we know the projective span of the Klein bottle. Amazing. We don't know very much else. There's this Annals paper where Auslander and Sharba solve this line bundle decomposition problem, or the line field problem, for compact solve manifolds. They show that every compact solve manifold is line element parallelizable. So that means that the tangent bundle of every compact solve manifold, it splits totally into lines. And this had some important consequences in the theory of dynamical systems and some other stuff. And I don't understand the methods that they used at all. They're really just not anything that I know or recognize. But this was a very important paper and something that we know about projective span. I also just want to quickly tell you what the projective span of spheres is. So we've seen the span of spheres. And if you're a real manifold and you're simply connected, which spheres are simply connected, by universal coefficients, you don't have any degree 1 cohomology, so you can't have any non-trivial line bundles, right? So if you're not comfortable with this, it doesn't really matter. But the point is, if you're simply connected real manifold, the projective span coincides with the span. And this is very simple to show. So it's immediate, really, that we know the projective span of spheres is the same as the span of spheres. So that's great. We know about the projective span of spheres. And we're pretty much done with known information about projective span. So now I'm going to tell you about some new stuff. I want to tell you a little bit about the projective span of quotients of spheres. I'm calling them spherical space forms. This is ongoing work with my advisor, Mark Grant. So this isn't written up yet, but I'm just telling you about this for fun, just because it's a cool example. So we want to just look at odd spheres, because if we have an even dimensional sphere, the Euler characteristic isn't 0, so we don't have any vector fields even. So we're going to look at odd spheres, and we're going to equip the sphere with a round metric. Doesn't really matter. Just have a little bit of group theory now. So this definition, I have a group G, and I want it to act freely and orthogonally on the sphere. Now there's a lot of work, a lot of literature about which groups can act on spheres, and it's a deep theorem that if your group acts freely and orthogonally on the sphere, the CELO2 subgroup of this group can either be cyclic or generalized quaternion. So this is like a major fact that I'm just black boxing so that this definition makes sense. But say I have a group acting like this, we will say that it's of real type if its CELO2 subgroup, which is unique up to conjugation, is trivial or is E mod 2. We'll say that it's of complex type if its CELO2 subgroup is cyclic of order at least 4. And we'll say that it's of quaternionic type if its CELO2 subgroup is a generalized quaternion group. Okay. So this is just a definition. Now Becker in the 1970s computed the span of these space forms. So these quotients of spheres where this group is acting freely and orthogonally. And there are some counterexamples to this statement when M is 8 or M is 16. So you're looking at the 7 sphere or the 15-dimensional sphere. Something really weird and wrong happens in those cases. But in all the other cases, if your group has real type, complex type, or quaternionic type, the span of the corresponding space form satisfies this formula here, where these are the Radon-Hurwitz-like numbers that I kind of mentioned at the beginning. So when F is equal to the real numbers, you get the regular Radon-Hurwitz numbers that we saw before. And there's some other ones. I just don't want to define them because then I have to explain some like representation theory of Clifford algebras and stuff. But they're these cool numbers, and this is like a really interesting result. And he uses some very fancy equivariant homotopy theory to prove this. And so for me, it's very natural to ask, what about projective span? We know the projective span of spheres. What about of these space forms? We've computed and not written up the projective span of the space forms for the real and complex type groups. We can't do the quaternionic ones, but this is just like an example of something that we can prove. So let's look at G is equal to Z mod 4. So cyclic group of order 4. That is a complex type group because its CeLO 2 subgroup is again Z mod 4. So Becker tells us what the span is of these things. And we can, so the way that we prove this example, so on the right-hand side of this, we take a specific group action of the Z mod 4 group on the sphere, and we take the one that we like best and the thing that we know most about. So we want to look at the usual mod 4 lens space. Okay, so we pick a specific group action, and we look at the mod 4 lens spaces, and we appeal to the diffeomorphism classification results about these mod 4 lens spaces, and we can prove this right-hand side here in that specific case. And then we have this kind of insanely powerful statement saying that somehow the projective span doesn't actually notice the details of the group action on the sphere. It just really only notices the type of the group. So we can sort of use our computation of the projective span of the mod 4 lens spaces and lift it to all of the other space forms with the same type. So anyway, this is just some interesting stuff that's coming up. Which time? Yeah, okay. So this is the last part of the second part of this talk. So far we've just been looking at this line bundle decomposition problem 1, which is about computing the projective span of the tangent bundles of manifolds. And we don't know very much about it. I've given you a few examples. And this is the next example is the main content of the first part of my thesis. I want to try and explain to you what the projective span of the wall manifolds is. The wall manifolds are built out of Dold manifolds. So I have to first tell you what the Dold manifolds are. And Dold built these manifolds as generators of the unoriented cobordism ring. So these are kind of major players in differential topology, because if you have some manifold, you're trying to study it and it's very, very hard. Maybe you give up a little and you look at its cobordism class. And now you have these Dold manifolds, which are generators of the cobordism ring. So maybe you can describe the cobordism class of the manifold you're interested in terms of these Dold manifolds. So if you know lots of stuff about the Dold manifolds, then maybe you can learn stuff about the manifold you actually care about, at least up to cobordism. So that's kind of the rough story about these Dold manifolds. The way you define them, you take two integers, m and n, both bigger than or equal to 0, and you take an m sphere, you cross it with CPN, and you quotient out by this Z2 action. And the Z2 action acts on the sphere by the antipodal map and by complex conjugation on the CPN part. It doesn't really matter. That's just how it works. So maybe just for a sanity check, you can't really visualize many of these Dold manifolds, but I can give you a few examples, a few trivial examples. So if you take n to be 0, CP0 is a point. So you're just going to have the sphere quotiented out by the antipodal action, and you'll get real projective space, right? If you take m to be 0, you have S0 cross CPN. So you have two copies of CPN, and then you're quotienting out by the complex conjugation action on CPN. Maybe it's not immediately obvious, but you can kind of see how this is going to be homeomorphic to CPN, probably. The only other Dold manifolds that I can possibly give you an idea as to what it is P12. So this guy, you can see easily, is the mapping torus of CP2 with respect to this complex conjugation thing. And it's a bit tricky, but you can prove that it's cobordant to the Wu manifold. Maybe you've seen the Wu manifold before. It's this really fun 5-dimensional manifold that has this nice description as a homogeneous space. So, you know, that's cool. These are the Dold manifolds. The wall manifolds are the thing I care about. And Wall built these as generators of the two torsion part of the oriented cobordism ring. So they're also interesting in that way, but they're mapping tori of the doled manifolds. So to build a wall manifold, you take a doled manifold PMN, you cross with an interval, so you have this generalized cylinder. At each end of the cylinder, you've got a copy of PMN, and you want to glue along a homeomorphism of the doled manifold. And the one that you pick is the homeomorphism induced by reflecting in the last coordinate of the sphere, the m-dimensional sphere defined coming from the doled manifold. Again, not really important to understand, but that's just what these wall manifolds are. They're really nice things, and the fact that they're mapping tori is very important. We were able to compute the projective span of these wall manifolds without knowing much at all about the span. So the projective span of QMN satisfies this formula here, 2 nu n plus 1 plus m plus 1. And nu n plus 1 is the two-adic valuation of n plus 1. So 2 nu n plus 1 is the biggest number such that 2 to that number divides n plus 1. That's what it is. And this is very intricately tied with those radon-Hurwitz numbers of real type that we saw earlier. I won't really go much into it, but the point is we have this nice compact formula for the projective span. And another nice thing is we got this corollary, which is quite nice. So if m and n are both even, then Carré calculated the span of these wall manifolds. This is some of the little information we have about the span of them. Turns out it's equal to 1. But our result tells you that you can actually split off, these manifolds admit m additional non-trivial line fields. And we really didn't know before that the difference between span and projective span could be arbitrarily large. This is just how little we knew about projective span. So this was a nice kind of proof of concept result. Okay, any questions so far? Yeah. Yeah, so I don't know about like exactly what relationship they have, but say you wanted to know the projective span of a manifold and maybe you couldn't really do it. You could say if you knew the projective span of these wall manifolds, you could figure out a description of the cobordism class of your manifold that you care about in terms of these wall manifolds and figure out the projective span of your manifold up to cobordism. No. Yes. Yeah, I'm pretty sure it wouldn't. Yeah, so yeah. Not amazing, but yeah. Yes, thank you. Any other questions so far? Okay, great. We're on to the last part of the talk now. So the second part was about this line bundle decomposition problem 1, and I just gave you a slew of example computations of projective span of manifolds. I really have caught you up with everything that we know. Problem 2 is a variant of problem 1, and there are more tools available in this case. Problem 2, if we know the answer to problem 2, it would help a lot to answer problem 1. Probably it wouldn't completely answer problem 1, but it would help a lot. So problem 2 is about characterizing the projective span of a given vector bundle in terms of computable invariants. What kinds of invariants? Well, the sort of thing that's going to be involved is the rank of the vector bundle and the dimension of the base space of the bundle, for starters. And it will probably definitely involve the characteristic classes or characteristic numbers associated to the vector bundle. And we'll see that we also need to know about the characteristic classes of the line bundles that you're trying to split off. It's a bit weird, but you sort of have to pick the line bundles you want to split off first. You'll see what I mean. This is problem 2, and the second part of my PhD thesis is dedicated to this problem. Now, I didn't want to assume that everybody knows what characteristic classes are, and probably this is just not going to help at all. But I'm calling this a crash course. It's really not a crash course. F still is either the real or complex numbers, and you want to give yourself some kind of cohomology functor. For me, this is basically always singular cohomology. It doesn't have to be singular cohomology. I don't even think it has to be an ordinary cohomology theory, but let's just give yourself a cohomology functor. And we have a topological space X, and I'll define V of X to be the isomorphism classes of vector bundles over this space X. Now this VF defines a contravariant functor, because if I have a map of topological spaces from X to Y, this F, I can pull back a vector bundle over Y along this map F and get a vector bundle over X, right? So this is a contravariant functor. And I don't think anyone would be too mad at me for defining a characteristic class to be really just a natural transformation like this. So to a vector bundle over a space, we are assigning some kind of cohomology class, which is natural. That's really just what a characteristic class is. So some kind of natural cohomological data like this. Okay, I don't know if this helps anyone if you've not seen characteristic classes before. But okay, so for this part of the talk, I'm really going to be focusing on complex vector bundles. So we're kind of just going to forget the real stuff now. So V now is going to be a complex vector bundle of rank M, and we're always going to have it as a bundle over a 2M dimensional CW complex. Okay, now complex vector bundles have these really nice characteristic classes called Chern classes. These Chern classes, the kth Chern class of the bundle lives in the 2K cohomology of the base space of the bundle with integer coefficients. And they satisfy this naturality property that I showed you before. So we can call them characteristic classes. But they also satisfy a bunch of other nice properties. And one of the great consequences of those amazing additional properties that they satisfy is that they are obstructions to the existence of linearly independent sections of the bundle, or they're obstructions to the existence of trivial subbundles of the bundle. So for example, you have some vector bundle and you look at its top Chern class. So the Chern class that lives in degree 2M cohomology of the base space. And that top Chern class, if it vanishes, well, if it doesn't vanish, then you cannot have a rank 1 trivial subbundle. If you look at the penultimate Chern class, so CM-1, if that thing doesn't vanish, then you can't have a rank 2 trivial subbundle, and so on. So if you have trivial subbundles of some rank, then a bunch of the Chern classes have to vanish, is basically the upshot. So if I know that the span of my complex vector bundle is bigger than or equal to R, we then know that the Chern classes of the vector bundle have to vanish in a certain range. You don't have to keep track of all the indices and whatever else. It's just very helpful information, these Chern classes. And I'll also tell you that there's this thing called the total Chern class, which is it's an element of the cohomology ring of X with integer coefficients. And it's just made up of all of the non-trivial Chern classes. I mean, this X is a degree 2M CW complex, so it has 0 cohomology above degree 2M, right? Okay, so that's the total Chern class. Now, what I'm trying to get across here is that there's a very natural, necessary condition for the existence of a R-fold like decomposition of your vector bundle into R lines. This is what I'm trying to show. So we have this complex rank M vector bundle over 2M dimensional CW complex, and we choose an integer R, which is bigger than or equal to 1 and less than or equal to M. And we try and split off R lines, the direct sum of R lines from our big vector bundle. If we can do that, then we have this factorization of the total Chern class that I defined earlier. for the complex vector bundle V. So maybe you can just believe me if this is a bit uncomfortable for you, but the total Chern class here must factorize like this in terms of the total Chern classes of the line bundles that we're trying to split off, and then this additional X. And this X has the property that it can't be made up of stuff in cohomology degrees higher than 2 times m minus 2r. So really the big picture here is we have this geometric thing, the fact that our bundle V admits a subbundle of R lines. And because that happens, there's some algebraic condition that must be satisfied. We're factorizing the total Chern class in this way. So we get this nice algebraic condition. But a priori, we really don't know if the reverse of this implication holds. And that's what I'm interested in. I just want to start with the fact that we have such a factorization. And if we have such a factorization, can I find conditions on the vector bundle or the base space of the vector bundle so that we can guarantee the existence of a subbundle like that? So I'm just looking for conditions under which the reverse implication of 1 holds. And here is the answer. The actual theorems in our paper, you can read it if you want. They're very, very long, and it takes like 2 or 3 pages to state the theorems because there's so many horrible conditions. So I'm just trying to simplify things a little bit, and I'm making the base space of the complex vector bundle a manifold. And the only reason I'm doing that is just because I want to use the fact that this manifold has Poincare duality, and that really helps me out. So I have this complex vector bundle of rank m, and the manifold is of dimension 2m. And in that case, we have some if and only ifs. So I'm going to explain to you some situations in which we have this reverse implication. So if m is bigger than or equal to 1, then I can always split off a single line bundle from my big bundle if and only if the Chern class factorizes like this, like I tried to explain before. So this was already known. I'm just putting this here for completion. But this is where the real work begins. So now we need to suppose that m is bigger than or equal to 3. And if m is even, we have to have another kind of weird condition. We need the second Stiefel-Whitney class of the manifold to not be 0. So this is kind of a bit weird, but the manifold here is, I'm not talking about the second Stiefel-Whitney class of the vector bundle over this manifold. I'm talking about the second Stiefel-Whitney class of the tangent bundle of the manifold, which happens to be the base space of this vector bundle. So anyway, there's kind of weird condition. Given that, then we can split off 2 lines from our bundle if and only if this factorization happens for the total Chern class. So we have this geometric thing happens if and only if this algebraic thing happens. And then when we start splitting off 3 line bundles, things get a little bit worse. We have to suppose now that m is strictly bigger than 5. We did try to extend this to hold for m is equal to 5 as well, and it probably can work. We couldn't quite do that just because of computational horror. But it's probably possible. But we have to have kind of high dimensional manifolds here. We need the manifold to be simply connected, and we need its second homology with integer coefficients to have no 2 torsion. And if m is odd, we have to have a bunch of other stuff. So given all of this, we can split off 3 lines if and only if the Chern class factorizes like this. So this is nice, and just to maybe make this seem less horrible, complex projective spaces, for example, if you look at complex vector bundles over complex projective spaces, they satisfy all the conditions of these theorems. So it's not super restrictive. There are many examples of manifolds that you can put as the base space of your vector bundle, and you can actually use this theorem. It's not as restrictive as it might first appear. The 0th Chern class is 1. Isn't that a problem for the time? Okay, let's see. Oh, I see what you're saying. So you're going to have like 1 plus something times x. Yeah, I mean, I guess this is going to be a problem for all of them, how I've written it. Yeah, this is a good point. I think, yeah, this is a good point. Thank you. I think maybe I need to write 1 plus on the other side. I think that fixes it. Does it? Yeah, but you're absolutely right. Yes, that's true. Okay, well, maybe I should also. So this x, sorry for writing on the dinner thing. I prefer to think of this x as the total Chern class of this stable bundle. So that you can think of this x as that. And in that case, it will have something like this. So actually, maybe the x just has to have a 1 in it, a 1 plus something. But thank you. That's actually a really good point. Yeah, I don't know if this makes sense, but yeah, okay. Yeah, thank you for these questions. Please interrupt me at any time if you have any other questions. I like questions. Yeah, okay, so this is this theorem, and we've worked a lot harder than this. You can look at our theorems when M is a CW complex. It's much more horrible and much more technical, and I don't know if anyone can use the theorems because there's so many conditions, but I wanted to just spend a minute talking about the proof. I think I have a few more minutes. The way that we prove this theorem is using obstruction theory. So I don't want to get like into the weeds or anything, but this is just a kind of a picture that I can talk around. So we define this fibration QMR, and it's defined in such a way that it's, first of all, its homotopy fiber is the complex Stiefel manifold. So this vertical thing here is a fibration up to homotopy. And I have here this vertical arrow. This is the classifying map of the complex vector bundle that we care about and the R line bundles that we're trying to split off. So we have this classifying map here. And this fibration QMR is defined in such a way that if we have a homotopy lift of this diagram, that lift will give you the existence of a monomorphism of L1 plus ... plus LR into the big bundle. So we can split off the direct sum of these line bundles from V if and only if there's a lift, a homotopy lift of this diagram. So we can phrase the problem as a lifting problem is the point, and we can use more Postnikov theory to try and solve this lifting problem. It's a very nice theory because what you do is you start with this input vibration and you factorize it into a bunch of a tower of vibrations. That's how you build a more Postnikov tower. And you have all these Postnikov pieces. And depending on the dimension of M, you just have to build a map from M into some high enough Postnikov piece. And if you can manage to do that, then you will get for free your lift of the original diagram that you care about. So that's kind of the very vague way that more Postnikov theory works. And to build the tower, you have all these K invariants, and the K invariants encode something about the obstructions to constructing this map from M into the high enough Postnikov piece. And you can learn something from the obstruction theory there. So the reason I wanted to tell you about that is just because when you look at these conditions, you might think, can these be improved? They can't be improved using this approach. The conditions that we have in these theorems are the best possible conditions that you can have using this method, except for this strict thing here. You might be able to improve that to hold also for M is equal to 5. But other than that, you need to use a different approach to get better statements. All of these conditions are artifacts of the proof method here, and they can't be improved. Okay, I just wanted to remark, I have a sort of modest application of our results to complex geometry. There's something called the Schwarzenberger condition, which allows you to design Chern classes of a complex vector bundle over CPN. So, I mean, the idea is you want a complex vector bundle over CPN with certain Chern classes. So you pick the Chern classes you want, and you ask, are they the Chern classes of a vector bundle over CPN? And they are the Chern classes of such a vector bundle if and only if they satisfy whatever this Schwarzenberger condition is. So using our theorem, we can kind of beef up the Schwarzenberger condition, and you can now design a vector bundle over CPN, which has decompositions of lines, you know, so you can get 1, 2, or 3 complex line bundles plus some other thing over CPN using our theorem together with the Schwarzenberger condition. Yeah, and that's all I wanted to say. Thank you so much for listening to my PhD thesis.
Can the theorem be perhaps stated better with diagrams or something, some categorical conditions? Like, is it complicated because you're forced to use text?
I don't know if you can. I don't know if you could state it in an easier way. It's a bit of a technical theorem, I guess.
Do you have any applications in mind other than the one you mentioned in the end, like for other spaces and to study vector bundles over it?
Yeah. Yes. So there's this area of Kähler geometry where you look at Kähler manifolds, and I don't really know why they do this, but you have this manifold and you look at its universal cover, and you sort of want to know about how geometric properties of the manifolds, how they translate to geometric properties of the universal cover and vice versa. And one of the things they care about is line bundle decompositions of these manifolds. So I think we could use this kind of thing to maybe get some results in that sort of area. Of course, you can just keep going and try and split off more line bundles, but the obstruction theory just gets really, really bad.
Thanks.
Thank you.
More questions?
So do you get this result by computing the cohomology of the quotient space of a Stifel manifold by the torus action?
Ooh. Okay, wait. Okay, so you the complex Stiefel manifolds.
Yes, the first one is just a CP infinity or something like that in the stable range. The second one is just a weighted product, I guess.
Yeah, I don't know, but that is really interesting, and I should think about that. Thank you.
Thank you.
Anyone else? No? Then let's thank Bailey again.
Good evening, everyone. First of all, I would like to thank all the organizers for giving me the opportunity to be present here and share our research work on shellability of cut complexes of powered cycle graphs. In this talk, I will first discuss some definitions, and basically I will cover all the terms mentioned in my topic, shellability, cut complexes, and powered cycle graphs. Then I will come to our main results, and will also discuss a brief outline of the proofs. At last, I will also discuss future directions. So I will start with the definition of an abstract simplicial complex. An abstract simplicial complex is a set A together with the collection delta, where delta consists of the finite subsets of A such that delta is closed with respect to taking subsets. The elements of delta are known as faces or simplices, and the maximal faces are known as facets, and dimension of a face is equals to its cardinality minus 1. Next is the geometric realization of an abstract simplicial complex. It is a pictorial representation of an abstract simplicial complex. Let delta be an abstract simplicial complex with vertex set V1 to Vm. Then for geometric realization, first we define, for geometric realization of an abstract simplicial complex, first we define the geometric realization of its simplices. So for this, we consider a map F from the vertex set of delta to Rm such that every ith vertex is mapped to the ith standard basis vector of Rm. Then for a simplex sigma which consists of the vertices Vi0 to Vik, its geometric realization is denoted by G sigma equals to the convex hull of the images of each of its vertices. Then the geometric realization of the abstract simplicial complex delta denoted by mod delta equal to the union of geometric realizations of all of its simplices. This abstract simplicial complex is a combinatorial structure, while its geometric realization is a topological space. So we topologize mod delta by defining a subset S to be closed in mod delta if and only if its intersection with G sigma is closed for each sigma belong to delta, and each G sigma has a subspace topology as a subspace of Rm. So one can easily see that these are the geometric realizations of the simplices up to dimension 3, and in higher dimension we can also get the geometric realizations. And here is an example of the geometric realization of the abstract simplicial complex given by delta. Next is the K-cut complex. As per my topic, the K-cut complex is a simplicial complex associated to a graph, and we define it is the K-cut complex for a positive integer k such that its facets, means maximal simplices, are those subsets of the vertex set of graph such that their complement is of size k and the induced subgraph on their complement is disconnected. Here is an example given a graph G, and we want to find a 3-cut complex of this graph. Then observe that for the set 1 to 4, its complement is of size 3 and the induced subgraph is disconnected. The complement of 1 to 4 is 3, 5, 6, and in that case 5 will be an isolated vertex, so the induced graph will be disconnected. So 1 to 4 forms a facet, and similarly we can find all other facets and given the geometric realization of delta 3G. Next is the motivation behind cut complexes. Cut complex, one of the main motivations of cut complexes is a famous theorem of Ralph Froberg that connects commutative algebra and graph theory through topology. Before going to the statement of that theorem, we need some terminologies, some definitions. First one is Stanley regional ideal. We define the Stanley regional ideal of a simplicial complex delta. It is noted by I delta such that the delta has vertex set V1 to Vn and given a field k. Then I delta is generated by square free monomials of the form xi1 to xik, such corresponding to the vertices vi1 to vik, where vi1 to vik is a minimal known face of delta. Next is a clique complex. Clique complex is another simplicial complex associated to a graph. Yesterday, Bravo also talked about independence complex. That is also an example of simplicial complex associated to a graph, and clique complex is also one of that. So a clique complex, the faces of clique complex are those subsets of the vertex set of G such that the induced subgraph on those subsets is complete. It means the any two vertices are connected. So it is easy to observe that the Stanley regional ideal of clique complex consists of square free quadratic monomials, because any known face of the clique complex must have at least two vertices which are not connected, And a minimal known face will consist of exactly 2 vertices. So this way we can find the Stanley regional ideal of clique complex. Now here is the theorem of Ralph Robert. It states that if I delta is the Stanley regional ideal generated by square free quadratic monomials, then I delta has a 2 linear resolution if and only if delta is a clique complex. Delta is the clique complex of a chordal graph. So this theorem deals with the quadratic square free monomials. Considering high degree square free monomials lead to the concept of K-cut complex. For that, we need another definition, that is of Alexander dual. Alexander dual of a simplicial complex is also a simplicial complex. It is noted by delta check, and its faces are those subsets of the vertex set of delta such that their complement is not a face of delta. So if we want to find the Alexander dual of clique complex, then it will be generated, or we can say its facets means maximal simplices will be complement of the size 2 subsets such that the vertices in that subset are not connected. Then it will be a minimal known face of clique complex, and its complement will form the maximal simplex of the Alexander dual of clique complex. Now recalling the definition of cut complex, we have the complement of those subsets which are of cardinality k, and the induced subset on those on the subset sigma is disconnected. Note that in case of clique complex, v1, vi1 and vi2 are not connected. It means the induced subgraph is disconnected. So in case of taking only 2 vertices, if we consider k vertices, then this concept generalize the idea of K-cut complex. And obviously the Alexander dual of clique complex is equals to the 2-cut complex. Next is the definition of shellability. Any given a simplicial complex delta with facets, then an ordering of its facets is a shelling order if whenever we add a facet fj, then its intersection with all the previous facets is a pure simplicial complex and is of dimension equal to the 1 less than the dimension of fj. And by pure simplicial complex, we means it's all the facets are of same dimension, and in our case the dimension of facets of K-cut complexes is equal to the n minus k minus 1, because the complement is of size k. So the cardinality of facets of K-cut complex is equal to n minus k, and its dimension will be n minus k minus 1. So K-cut complex is also a pure simplicial complex. Here is example. We have 2 examples of shelling order. Both of these are shelling orders, but these 2 orders are not shelling order. Next is spanning faces. If the given simplicial complex is shellable, then the its facets are those facets are known as spanning, whose boundary is contained in all the previous facets. So we can see this by an example. Suppose we choose this order f1, f2, f3, f4, then the boundary of the facet f4 forms a triangle 2, 3, 4, and it is already contained in the union of f1, f2, and f3. So f4 will be a spanning facet. Why I am talking about all these? Because this shellability has a very important consequence. If we have a shellable simplicial a pure shellable simplicial complex, and we also know about its spanning facets, then we can tell about its homotopy type. Then delta will be homotopy equivalent to vase of beta spheres of dimension sd, where d is the dimension of delta and beta is the number of spanning facets in that shelling order. Next is the definition of powered graph. Given a graph G, then it's the powered graph is denoted by GP, the vertex of the powered graph is exactly same as the graph G, and in powered graph, any two vertices U and V are adjacent if and only if there exists a path of at most length P in the graph G. The next is the definition of cycle graph. The cycle graph has vertex set, the cycle graph for n vertices has vertex set 0 to n minus 1, and every ith vertex is connected to I plus 1th vertex, and the last vertex is also connected to the first vertex, and hence we get a cycle. Here is an example of a cycle graph on 9 vertices. Note that the distance, the path between the 1, 2, 8 and 7 with 0 is of at most length 2. So in squared cycle graph, 0 is connected to 1, 2, 7 and 8 also. Similarly, we get this complete squared cycle graph, and we also get this 3-powered cycle graph. Now let's come to our main result. In the article Topology of Cut Complexes, Ware et al. Introduced the cut complex, and they conjectured about the k-cut complex of a squared cycle graph. They conjectured that the k-cut complex of a squared cycle graph for n greater than or equal k plus 6 is shellable, and they also conjectured about the homotopy type of 3-cut complex of squared cycle graph. We proved this result for k equals 6. We proved that the 3-cut complex of squared cycle graph is shellable, and we also proved it homotopy type. Moreover, we have some partial results for k belongs to 4, 5 and 6, but in our case we have n greater than or equal 2k plus 6. The result we proved for 3-cut complex of squared cycle graph, we extend it to the powered cycle graph, and we found that the 3-cut complex of powered cycle graph is shellable. We also obtained it homotopy type, and we have proved these results, which this article is in preparation and it will be available very soon on at this archive. So now come to the proof. We discussed about the shellability and spanning facets. So in our case, we define a order and prove that that order is a Schelling order. After proving that order to be a Schelling order, we found the we characterizes the spanning facets, and then we get that the 3-cut complex of powered cycle graph is homotopy type to this. Next result, we have proved the 3-cut complex of powered cycle graph is shellable, but we also explored the 2-cut complex of powered cycle graph. In that case, we found that in each of the cases, the homotopy equivalence, it is homotopy equivalent to a sphere of dimension less than the dimension of the 2-cut complex. And that's why in each of the case, this complex is not shellable. To prove this, we use acyclic matching. So first I would like to define what is an acyclic matching. Given a set X and delta be a finite family of finite subsets of S, then we define a partial matching on delta that consists of ordered pairs of delta such that if sigma and tau belong to M, then tau covers sigma, which means that there exists no element rho in delta such that rho is contained in tau and rho contains sigma. Moreover, every subset of delta belongs to at most one element in M. And it is easy to note that if M is a partial matching on delta, then there exists a subset delta prime of delta such that and an injective map mu from delta prime to the complement of delta prime such that its image, the image of the elements of delta prime covers its elements. Next is acyclic matching. Acyclic matching is a partial matching such that there does not exist a cycle given here. Note that its first and last elements are same. So it will be a cycle, but we don't want such cycles to have an acyclic matching. And those elements which are not matched in acyclic partial matching are said to be critical. So there is an important theorem given by Foreman, given a simplicial complex delta and a matching and a acyclic matching on delta, then delta is homotopy equivalent to a cell complex denoted by delta C, which contains exactly C, which contains all the critical cells with respect to the matching M in for dimension I. We consider that it has Ci critical cells, and also if we match the empty set, then we consider one more zero dimensional cell. This is a corollary that if an acyclic matching on a simplicial complex delta has faces only a fixed dimension I, then it is homotopy equivalent to a wedge of sphere in that dimension. So using these two theorems, first we construct an acyclic matching on the on the faces of two-cut complex of powered cycle graph, and we found the critical cells, and using these two results we compute the homotopy type homotopy type of two-cut complexes of powered cycle graphs. So now it's the time for future directions. We have computed the three-cut complexes of powered cycle graphs, two-cut complexes of powered cycle graphs, and where at all conjectured about the k-cut complexes of squared cycle graph. For three-cut we have proved, but it is still open for k greater than equal 3. Also, where at all conjectured about the homotopy type of three-cut complex of squared cycle graph. Computing from Say's calculations, we found that the k-cut complex is homotopy equivalent to this wedges of the spheres of n minus k minus 1. So yeah, moreover we also explore the powered cycle graphs for k-cut complexes for k greater than equal 4 and p greater than equal 3. In that case, we found that the non-trivial homology groups, we obtained the non-trivial homology groups in dimensions less than the dimension of this k-cut complex. So it lead to the question that whether these complexes are not shelleable, and if they are not shelleable, then what is their homotopy type? So one can try to prove this, or also the k-cut complexes are recently introduced in 2023. So there are many graphs which one can deal with, and other than shelleability, there are many problems that one can go for. These are the references. Thank you.
Thank you, Jason, for the introduction. Thank you to the organizers for the opportunity to talk here. So yeah, this is the project that was carried out during the past year with this group of people. Firas was a postdoc with me in Milano. And then we also worked with professors Alberto De Nunzio and Luciano Margara. And okay, let's do my kata thing. So the application part is clear. We're going to see a lot of it. Then well, to do this cryptography application, we're going to be playing around with functions defined on string of characters. So the combinatorial bit is there. And the topological part is in parentheses because we did use some topological arguments in the proofs of the theorems. But in the interest of time, I'm not really going to get into the proof of results in this talk. But if anybody is interested, I am happy to share more details. So, okay, what's the pipeline? Well, it's like very simple. It's the same one we used in elementary school to send messages to our friends. So we have our message. We have an encryption system to create some ciphertext. And then our best friend has a decryption system to be able to figure out the plain text. So in math words, what are we looking for? So we're looking for some function f that is not too easy to guess, because otherwise the teacher is going to figure out what the message is. It's chaotic enough to, well, make things more complicated. And then it has to be invertible so that the person who receives the message is going to be able to actually read it. And okay, in this specific project, we want to figure out in which case this f, in which case we can use something called a cellular automaton, which I'm going to define as this encryption function. So this is the plan for today. We're going to give some basic definitions and just give a name to the tools we're going to use. And then we're going to study how to introduce in our encryption function some chaos, but not too much, because we want to be able to control how much of it we include. And then we're gonna, study when the function we define is gonna be nice enough to be inverted. So, okay, the tools we're gonna use are very simple. So we need a message. So we're gonna need an alphabet. A basic one, well, a common one that is used is just the binary alphabet 0, 1. In this talk, we're gonna use the integers modulo m. Then a finite word is just a finite string of symbols with this alphabet. An infinite word that we're also going to call a configuration is just an infinite string, so an element of a to the z. And then we're going to denote with this like double square bracket a subword of an infinite configuration. So that's the like 4 tools we're going to need. And then the main player, the cellular automaton. So what is this? It's cellular automaton is a map that takes an infinite string and sends it to another infinite string by acting on subwords every time in the following way. So let's see an example. Let's say we have the XOR function, and so for every three symbols A, B, and C, we're gonna generate one output that is the XOR or the first 2 symbols. So this is what we're gonna do. So we're gonna start from here, and so little f, the local rule, is gonna act on the first 3 entries and generate 0 because 1 XOR 1 is 0. And then we're gonna shift by 1 and proceed in this way. And so we generate 1 bit of the image configuration in this way. And okay, that's one example of cellular automaton. Another very famous one is the shift operator that just basically takes our string of characters and shifts it by 1 bit. So that's what's going to happen. We just move everything to the left by 1. And if we plot it with some nice program, that is what the shift operator is going to look like. So, okay, that's the kind of map we want to try to use to encrypt our message. What's the problem with the examples we saw until now, the XOR and the shift? They're both linear. So the first like thing we asked our function is that it was like not too easy to guess. So linear is not going to be like good enough. We want our local rule to be nonlinear, but okay, nonlinear means everything. So just to start, we're gonna restrict our analysis to this subset of nonlinear local rules, and we're gonna call them LR separated. because, so basically, okay, remember from here, the local rule defining a cellular automaton was acting on a finite string every time and generating 1 bit. So in here, what we're asking is that the first variable appearing in the expression of the local rule is separated, and also the last variable is separated. These variables in between, they can do whatever they want. We can have like mixed products, we can have anything. The only important thing is that the first one appearing on the left and the last one appearing on the right are separated. So we're gonna concentrate on this form of local rule. And so, for example, this is what our rules will look like. If we have just monomial, that's going to be fine. If we have something like this with the mixed product in between, that's also going to be okay. All right. And right, so okay, we we decided how to encode the first property we wanted, the not too easy part. So let's now introduce some controlled chaos. So the way we're going to do it is we're going to ask our rule to be permutive. So what does permutive mean? So a function is permutive when if all variables are fixed except one of the external ones, then our function acts as a permutation in the external variable. So that's basically what's going to happen. If our function in this case is right permutive, then it means I can put whatever values I want inside of x0, x1, x2, x3, and then the value of a is gonna completely determine the output alpha. That's the thing. Now, why is this controlled chaos? Well, because it is possible to prove that these permutive rules are sensitive to initial condition, like because these external bits determines my output, then whatever little change of information I put here, it's gonna propagate in time every time I apply my function. And so that's gonna affect the final output, but knowing what I did here, I should be able to go back and recover the initial configuration. And so the result we had is that if we have our kind of local rule, so this left and right separated function, then our cellular automaton, our rule is right permutive, so the rightmost bit is gonna determine our output if the exponent here of the rightmost variable is coprime with the Euler Totient function of our ring Zm. So basically, the idea here is that if this bit is a bijective function, then the whole cellular automaton is right permutive, and so only the nice thing is that only asking that the tiny thing producing my output is bijective is going to help me introduce like enough chaos in the whole evolution of my rule. And remember that here my variables can be doing whatever. I don't really care. Okay, so this was the our second request, that we had enough chaos. Then the other thing we wanted is for our rule to be invertible. So well, the thing is we had some difficulty studying reversibility all at once. So we're gonna I'm gonna show you the intermediate result we got about surjectivity before moving to the invertibility result. And so, okay, first thing, what kind of result are we looking for? Like, what are the known theorems for linear cellular automata? And so the things that were proved about, so a linear cellular automaton is just a cellular automaton such that the evolution rule is a linear function, and the results that were showed are that a linear CA is surjective if and only if there is this coprimality condition, this kind of, if you will, orthogonality condition between all the coefficients and the dimension m of the ring. And then also we know that every permutive CA is surjective, and so in some sense this surjectivity is implied by chaotic properties. So the thing where we focused is this first result because it's an if and only if. So we looked now in our case for a similar result connecting the coefficient, and in our case also the exponents with the of our rule with the surjectivity condition. And the result that we got is a partial characterization of surjective rules. So what we proved is that if our cellular automaton is left or right permutive, so basically if either this exponent or this exponent is coprime with the Euler totient function of M, then F is surjective. So like we know that I mean, this is like nice enough. We know that if we force our rule to be to have either this bit or this bit bijective, then we're going to have a surjective something. But it would have been nicer to have like a complete characterization. We are very close to have one in the case of a finite field ZP. So empirically, we have this if and only if, so that our cellular automaton is surjective if and only if one of these two conditions hold. So we tried it for until Z211, something like this. So we are pretty sure it works. And but yeah, we are missing a little something to have the definitive proof. And yeah, I hope we're gonna be able to post this result for finite fields soon enough. Right. So at this point, the thing we know is once we have this kind of rule, if either this or both actually are bijective monomials in ZM, then this guy is going to be surjective. So the injectivity condition in principle is going to be something a little stronger. And okay, let's so okay, the again, the known result in the linear case are that F, the cellular automaton is reversible basically if and only if it is injective, and this is, well, not only in the linear case in general, so that's something we wanted to use. And so we were looking for a result saying something like if both are bijective, both bits are bijective, or only one is bijective, then it's going to be invertible. Unfortunately, what the result we found is that our kind of cellular automaton is injective and therefore reversible, if and only if we only have our local rule only looks like one monomial. And I say unfortunately because for cryptography application, this is not great. I mean, if you take like your ring big enough, then there are like so many choices for the coefficient AL and the exponent QL. but still, I mean, this is not some extremely complicated function. So like, it's good that we have this if and only if characterization, but the final result wasn't what we were hoping to achieve. And right, so these are a couple of examples to to show that. So for example, these two local rules are both both produce surjective cellular automata, but if you apply them to, in this case, the sequence 5656 and so on, and 4343 and so on, you get the same output. And the same happens here. In this case, we also have two counterexamples showing that the rule is not injective. So, and the problem is that we don't have a monomial. So like you always can find two infinite configurations that end up in the same configuration. And so what is the conclusion here? So we were able to find a partial characterization for surjective CA, and we're very close to the complete characterization in the finite field case. We do have a complete characterization for the reversible CA, and only shift like, meaning only like monomial functions are can be inverted. And so questions for the future, the first question is it possible to find a less trivial class of cellular automata? Because as we said before, that kind of function is not really like complicated enough to serve as a cryptographic one. And can we extend them to broader classes, like non-uniform cellular automata are just are like the cellular automata we define, only at every step you can apply different rules, different local rules, depending on a condition that's defined in at the beginning of the construction of the dynamical system. And also what happens in the case of an infinite alphabet. So the truly infinite alphabet is not really used in application, but it's like theoretical results about infinite alphabets then are useful in case of like huge alphabets that are used for example, what's it called? Password encryption, that kind of thing. And this is the preprint we posted on the archive, and that's all I wanted to say. Thank you very much. Mm-hmm. Right, yeah. Wait, here. So like to generate this, you want to take like these two guys and these two guys. Possibly, yes. I mean, the only thing is that you should do it in a uniform way. Like you decide that to generate, I don't know, like y3 here, you're gonna take x0 and x1, and then x4 and x5, and then you shift everything by one. So I mean, I believe in principle it can be done, but you cannot take like you cannot randomly pick at every step different, like, yeah, right. No, I think that's gonna be similar, because the thing is, in this function, you like the two players that really matter are this guy and this guy. So in principle, this, I don't know, let's say this is x1 and x11, so it's generating the middle one, so x5. These two guys can be x2 and x7. So I don't think, even if you take these joint neighborhoods for this kind, for this family of rules, I don't think the result is going to change. Well, yes, yeah. Mm-hmm. I'm sorry, say it again. Yeah. So right. So the thing is, sandpiles are like two-dimensional cellular automata, because you have like you have your like input here, and then like if you're using a square grid, this input fires in these four like adjacent squares. So we are not quite at the two-dimensional case with that with this project, but it should be like interesting to check.